Welcome to AUT-128 station number 4. This is Automotive Starting Systems, if the big starting picture there didn't actually tip you off. So before we start, as always, make sure that you have a packet that matches the one that I have here. It should say Auto 128, station number 4. It should have Automotive Starting Systems on it. It should have a starter on the front page. Make sure you have the packet, because you're going to have to read through the packet and follow along. Spend so much time writing that beautiful packet. It would be a shame if you were to continue on without it. So once you got it, we'll rock and roll. Learning tasks, as always, we're going to concern ourselves with our learning tasks. So in this case, we have to understand and explain the basics of electromagnetism. Got to understand and explain how relays and solenoids work. Got to understand and explain how the starting system itself operates, and then how do we test and verify the condition of the automotive starting system. So this is a pretty heavy chapter. So it's going to be a big section. We're going to cover a lot in this, especially electromagnetism. So make sure you hunker down, because it's going to be a long haul on this case. So let's move on to the safety section, because boy howdy do we love safety. So safety, as always, work with a low voltage system. Be aware of the shock that can occur. Be aware that you need to get all the jewelry and loose hair out of the way. We're dealing with spinning starters. They are very heavy on some of these models, and they do carry a lot of current, upwards of 250 amps. They can hurt you. We got to deal with batteries. So again, watch the sulfuric acid. It can burn you. It can burn your eyes. It can burn through your clothes. It can burn your hands. As always, if you don't know how something works, if you don't know if you're doing something right, stop and grab lab staff. Be sure to follow directions in this video for safety purposes. That way we do not get you hurt while you're working on these. Usually it's pretty safe, but a couple dundery, stupid mistakes can end up hurting you very badly in this section, so tread carefully. So, let's finally start. So, starting system. So the starting system breaks down pretty easily. The first and foremost is we have the battery. Everything starts and ends at the battery. If you've taken station 2, which I believe is a battery station, that means you know how important the battery is and how to check it. This is what you need for a starting system to work. You need a battery to start out with, and then we're going to have, you'll never guess it, it's the starter itself. Typically somewhere in there is some type of relay called the starter relay. These are the three major components. You got the battery itself, you have the starter, and then you have the relay for the starter, which is typically attached to the top of the starter. If the battery is good, then it sends power to the starter, which rotates, and we have the relay, which is usually what connects the two of them. The relay sends battery power down to the starter so that it can turn. So these are the three major components we're going to deal with. All of them, save for the battery, deal with electromagnetism. So before we do anything with starters, I'm going to run you guys through magnetism. So we're going to deal with magnets here first. So magnet is anything that exerts, get this, magnetism. Anytime we define magnetism, we define it as the ability to attract certain types of metal. We typically deal with iron, steel, or cobalt. Magnets themselves have 2 points. We typically depict them as square. We call them poles. We call them North Pole and the South Pole. Opposite poles of the magnet attract to each other, while similar poles tend to push away. So if you have magnets, they're objects that pull objects towards them or push objects away. Depending on their orientation, if we have a north end of a magnet and a south end, and they end up butting up against the north end of another magnet, what happens is they tend to push away from one another. However, if on my left side we do the same thing, we have the south end and a north end, and we put it butted up against the south end and the north end of a magnet, now the magnets have a tendency to pull towards each other. So instead of pushing away, they're going to drag into one another. If you look at my fancy picture right there on page 3, you should see the lines pulling into one another. So the reason this type of attraction occurs is because magnets are going to exert what we call flux lines. Magnetic flux lines. So if we take a magnet, take the north end and the south end, what they exert out of them are these little lines, invisible lines of force known as flux lines. So they tend to go in this rounded shape, so they tend to make this little oval shape out of the magnets, and the flux lines themselves are what we think of when we think of magnetism. So anything that gets caught inside the flux lines gets attracted to the magnet. The more flux lines, or the farther the flux lines go out, the stronger the magnet. So if we have an earth magnet, like a big stick magnet, the bigger and fatter the magnet is, the more flux lines it tends to have. All objects that can be exerted upon by magnetism, again, like cobalt and iron, if flux lines get close to them, they are affected, and they'll start dragging in or pushed away. No object is impermeable to flux lines. If I put a flux line against a thick door and it's strong enough, it will exert flux lines through any material whatsoever and pull a metal object through the other side. Some objects can resist flux lines, sort of like resistors in a series or parallel circuit, but nothing is impervious to them. They can go through things. This is why you can put a metal object on the other side of a swing door, and you can put a strong magnet on the other side, and you can hold the metal object to the door using a strong enough magnet, because the flux lines, like wavy lines of force, will cut through that object and pull through them. So flux lines are the lines of force that drag things in, and what we can do when we deal with different magnets is we can actually make these flux lines stronger. So what they discovered through physics is that if we take a magnet, like a permanent magnet, and we take copper wire, and we wrap this copper wire around the outside of the magnet, and we run power to that copper wire. It doesn't matter. It could be 1 volt, it could be 12 volts, it could be 500 volts. In my example, I'll use 5 volts. What happens is, and I'm going to draw one side by side. So here's my normal magnet, unabated by any kind of copper wiring, and it's going to put out flux lines. So it's got some pretty decent flux lines. Here's my 2. It's going to be like that. Once you send power through the magnet itself, it's going to make the flux lines go out farther, and you're going to get more of them. And again, this is going to be in a big cone shape. I should say a big cylinder shape. It's going to be big and round. The more power that we run through there, so I have 5 volts, I'm going to change it. I'm going to up it to 10, send more power through it, and guess what? Look how much bigger your flux lines get. They get nice and wide. The more power that we send through the wiring, the bigger the magnet is going to get. So this is how we can use copper windings and electricity to increase the field strength of the flux lines. Again, copper wire wound on the outside of the magnet, once we run current through that winding, it's going to make the flux lines bigger. And that means any metal objects that are floating anywhere near here are just going to get dragged into or pushed farther away from the magnet with greater force, depending on whether they're north or south pole object. So more flux lines equals bigger magnets, which means more things get affected by it. You can see this if you've ever been to a junkyard and you see that big swinging magnet crane. The idea is that it swings over metal objects and it doesn't pick anything up, but when the controller in the booth flips on the power and it sends 200 volts to the magnetic coils, what they're doing is they're sending power through those windings, and now it picks up everything from engine blocks to cars. They move it to where they want to go, they flip a switch, it kills the current to the copper windings around the magnet gets weaker, can't hold on to the objects, and those objects drop down where we want them to go. This is how we can use electricity to increase the field strength on magnets to make them stronger. If you look at page 4 on your handout, I have the 3 other discoveries that they've made concerning field coils or coil windings. So basically, the first one is more windings equals stronger magnet. So for example, in the corner over here, if I have 2 magnets, here's one, here's my second. If I draw, here's whoop whoop, just like that. There's my windings. If I take and I put more windings on it, this will make a stronger magnet when it turns on. So the more windings that go around the outside, the stronger the magnet will become once we run current through it. So the number of windings around the magnet makes a big difference. That's the first takeaway. More windings equals stronger magnet once we turn the power on. The second is more amps equals stronger magnet. That's important too. So even if we keep the windings the same on two separate styles of magnet, so you take just one loop and run it down. If we send more power, more amperage through one than we do the other, and how do we increase amperage if resistance is the same? Yeah, you remember from station 1, got to increase voltage. That means that we will create stronger magnets in comparison. So more amperage, i.e. more voltage, goes through the same number of windings will make the magnet stronger. So we can increase windings and send the same amount of voltage to make a magnet stronger. We can also increase amperage / voltage and increase the strength of the windings as well. So more voltage, more amps, more power, more windings, more power through the magnets as well. Let me erase this all away. And the last one, if you reverse the current, you reverse the magnet's polarity. Very, very, very important. Must remember the last one above all else. So if I have a magnet, and I have one, this is north, and this is south, I'm going to make them both here. And again, I'm going to run my windings through them. So I'm going to make this the ground, make that the power, and do the same thing over here. However, I'm going to make this positive, I'm going to make this the ground. What's going to happen in this case is this will flip the polarity of the magnet. So running current through the opposite direction on the windings is going to flip the polarity of the magnet itself. So if we normally have an earth magnet that's north to south oriented when we set it on a table, if we wrap coil windings around it and then reverse the direction of the current, we change where the positive and negatives are because we're positive here and negative here, and then I switch that and I drag the negative here and the positive over here. That will reverse the poles of the magnet. And remember, this is important because the same ends of a magnet, north and north, push away from each other. South and south push away from each other. But if north and south ends of a magnet are pointed towards each other, they will pull towards each other. They will attract one another. Very, very important. So we're going to be using this a lot when we deal with generators, i.e. alternators, and starting systems. Got to know how to reverse the polarity. So with the basic principles in mind of magnets, how to make them stronger, and then how to flip their poles, we're going to start applying this. So if you move to page 5, we're going to touch on relays. So one of the most common uses for magnets inside an automotive system is to use them for relays. And a relay is what we call electromagnetic switch. And what it does is it allows us to use a small amount of current, small voltage, small amperage, and use a magnet to flip a heavy-duty switch that can flow lots of amperage and lots of voltage. The relay itself does work off that principle, and it has two sides to it. So if we look at our picture here, we're going to see a magnet. I'm going to draw you one in a little diagram right here. So here is my magnet. There's that. I'm going to run coil windings around right there. And then I'm going to have a little setup right there. And this is my spring right there. So what I have, if you look at page 5, I'm going to number these. So this is going to be 85. This will be 86. And the ones on the bottom are going to be 30 and 87. So that's the diagram that I have for my relay. The top part of the relay of this diagram is what we're going to refer to as the control side. The bottom part right here is what I'm going to refer to as the power side. As the name semi-imply, the control side controls the operation of the power side. And here's how it's going to work. I'm going to draw a simple magnetic switch on the other side. So I'm going to make this a bit faster. This will be a bit more crude. So again, we have our windings right here. And what's going to happen is, if I have this side, which is blank, what I'm going to do is I'm going to send power to this. So I'm going to take this side. So I'm going to take 5 volts right here. So we have power. Yes, we do. So we have power right here, and we have a ground right there. So that means this is a complete circuit, and that means we should get power to flow through it. And what I can do with that is once power flows through it, it's going to send current through these field windings. And when it goes through the windings that are wrapped around the magnet, what happens to the magnet? Magnet gets stronger, right? Without any power, the flux lines only go out so far. Once they receive the 5 volts I put into them, the flux lines get even bigger. And notice how they're now going to intersect with this switch right here. So they're going to intersect with this switch that I've placed. This is a metallic switch, and it is typically made from some type of iron or steel. And what happens is it's going to take the switch and it's going to push it down, and it's going to contact this part and that part right there, because the magnetic force is going to drive the switch down, which is what we want it to do. So that way what's going to happen is now we get ourselves a complete circuit. So that means the power side is now complete. So long as we energize the top section, as long as we energize the control side, which is again right here, as long as we send power there, that switch will stay closed. This is exactly what we want it to do. The moment we take power away from it, so we're going to take power away, that switch is going to flip back up. Because as I've drawn in my other picture, you'll notice that there's a little spring here. So typically there's a spring that's going to pull it, or push it, I should say, back out of place. And that's going to break the circuit. As soon as you send power back through the control side of the relay, you're going to get this to build back up again. It's going to intersect. The magnetism is going to drive it down and complete that circuit, which is what we want it to do. So now the circuit should be complete once we've done that. So this is how we're using the control side of a relay to close the switch or complete the circuit for the power side of the relay. So this is very, very important to us. So we're going to go back and let's take it like this. So let's imagine that we have 85 to 86, which is just going to be 85 to 86 right here. Anytime you send power to that, it's going to close the switch and complete the circuit to 30 to 87. The reason we have this rather than just having a toggle switch is because the control side is designed to use very, very little amounts of voltage. So this is going to use anywhere from 1 volt to 5 volts. So I'm going to draw my line right there for my control side. And it will draw very, very little amps. So it'll draw like 0.2 amps, which is very, very small amount. So we can have 1 to 5 volts, and it will draw 0.2 amps, which is insignificant. Remember, the battery itself tends to hold 400 or 500 amps, so this is a very small amount of draw. The difference is that the power side, or power side down here at the bottom, has a tendency to use up full 12 to 14.6 volts, and it for a starting system can draw 100 to 300 amps. Now, if we remember from station 1, amperage is the movement of electrons across the wire. So if we move more amperage, the wire is going to heat up even hotter because that's a lot of friction. That's an insane amount of amperage. This is why your battery cables are incredibly thick, while most of something like a speaker wire tends to be pretty thin. You'll notice on the battery cables on a vehicle, they're very, very large because they have to carry a lot of amperage. If we were to just wire a switch from the computer down to the starter, that wire coming out of the computer would have to be a very, very large wire, which is not really conducive to keeping wires nicely packed and tucked away inside the hood. So we need small wires. So what we have in this case is we can use incredibly small wires right here to handle a small amount of large wires right there. So that's why we have relays. Anytime we want to control when we actually have a very large amount of voltage or amperage moving through something, and we want to use something very sensitive like a computer or an ignition switch, we need to have a relay in its place. Imagine that this side of this circuit carries 300 amps. That means if we didn't use a relay, we would have to pump 300 amps through the ignition switch, which is where you put your key in your car. That's insanely dangerous. That lock cylinder would glow red hot and you'd burn yourself. But not if we use a teeny tiny wire to turn on the control side of the relay and go from that point. So this is why we have relays, and this is our most common use for electromagnets that we will find. You'll find this in houses, you'll find this in automotive uses. It's very, very common. All relays work off this principle. You should have them numbered roughly the same, 30 and 87, 85 and 86. So that's how it's going to work out in that case. I'm going to show you in principle right here. We're going to move on into the lab. I'm going to show you how to hook up this relay, and then we'll go from there. So go ahead and follow on the next part of the video.
All right, so now that we've run over all the theory and the whiteboard and we've run it into depth, we're going to have you stand in front of our fancy physical relay board and have you guys set one up for yourself. So in this case, we're going to be using one of these standard relays. Notice that on the top that we still have a wiring diagram, just like I promised. You got 86 to 85, which is going to be your control side, and then you've got yourself your 30 to 87, which is your power side. Simple and easy, right? You got the pins on the bottom here that are going to give you your pin out numbers. So if you notice here at the top, we got 87. You're going to notice at the bottom we have 30. On the side, we've got 85 and 86. So if you're ever in doubt which pin's doing what, you just got to flip it onto its side and check the pins out, all right? Same thing for the diagram. The diagram on front is going to direct you for your control side and your power side. It's enough talking. Let's go ahead and set it up. It's going to be using our fancy electrical board right here. You should have a power switch down so. Press it to make sure it's off, or flip the switch down to make sure that it's off. We're going to use is the pin connectors first. Spade connectors just like in station 1. If they're not in there already, make sure you put them in there yourself. Just got to run them through just like that. Put one in for the power side, which is going to be on the left. Put one in for the ground side, which is going to be on the right. Just one at a time. So what we're going to do first is we're going to wire up the control side, which again, if we're looking at it, control side is real simple. Just going to run it in, 85 to 86. We got to check our pin out. So we have 85 on this side and 86 on this side. If you're not sure, just got to bring it in, take a look. Man, that's blurry as all get out. So we're going to run a pin to 85. So run power, just like that. That's going to be your power into 85. All you got to do is ground 86. So we're going to take it to the ground, set it right there. Run it to the ground side on our electrical board. So I put the spade connector there. You should be able to flip the switch. You should hear it click. Yes, you should. You should hear the relay click right here. Take your fingers, run it on, flip it. You should feel the relay click over. Again, what's happening inside of there is you're actually getting the magnet to power up because you got flux lines, and that's what's going to shunt the control side and shut off the power. So what's going to happen is it's going to drive it out and close that switch. So that way we power up 85 to 86. It closes the switch 30 to 87. That's all we have for the control side. Simple and easy. Power comes in, ground goes out. That's it. Pretty simple stuff, right? So what you're going to do in this case, we're going to break it down. Let's break our wires back down. I'm going to have you set up the power side next. So setting up the power side is pretty similar, slightly more complicated. What we're going to do is we're going to check our diagram again. So you got 30 to 87. Flip it. You see the 30 pin right here on the bottom? You should see the 87 right here at the top. So power in, power out. Simple, right? Look at that focus. So we run power in just like we normally do. We're going to run it to 30. Then we're going to run from 30 through to 87 and run that power over to the light bulb. As always, we need to make sure that we ground the light bulb out, because if we don't have a complete circuit, nothing turns on. So all we're going to do is, just like in station 1, you got to ground out that light bulb to the pin connector right there. And that's it. See how simple that is? All we're doing in this case again, so we have power coming out, goes up to pin 30 on the relay. When we turn the relay on, 30 will connect to 87, which will run power to the light bulb, which will receive power and then ground out and turn on. Simple and easy, right? So you should have this set up right now. So what we're going to do is we're going to move on and we're going to reconnect the control side, and it should all turn on. So let's go ahead and wire up the control side so we can see it all work in magic. So I'm going to use a green wire this time because it's pretty, because I like pretty green eyes. And you have your spade connectors right here. If you don't feel comfortable connecting off that spade connector like I don't, you can just run another one. So all you should be doing is just take another spade connector, kind of move this out of the way. Going to run a spade connector for power. And we're going to run a spade connector for ground. So there's my other ground connection. So I'm going to take power. We're going to hook it up. Let's run it to the control side, to the right, to 85. So it's going to go over here to 85. So that's in. And then all we're going to do is we're going to ground out 86. Take the ground connector, connected to ground. There it is. Got your power switch down here, whether it's a button or a switch, hit it, light should turn on. Look at that, first try. Isn't this so very nice? Turn it off, turn it on. So pretty, I love it. So that's all you gotta do. Same thing, you should be able to feel the relay click over, the light bulb should turn on. If the light bulb doesn't turn on, you need to check your power side connections. Make sure your power connectors are connected right onto the relay. If you forget, all you gotta do is look at the top of the relay again, and you'll manage to see what you're doing. All we're doing is we're going 30 to 87. In 30, out 87 to the light bulb. Make sure you ground out the light bulb. Our diagnostics is, if it flipped the switch and it doesn't turn the light on, if the relay clicks, that means you got the control side hooked up right. It means you got to check your power side. If you flip the switch and this doesn't click over, that means you hooked up your control side wrong. So double check what you've got. If you flip the switch, the relay clicks on, the light bulb turns on, you are done. Go ahead and get a sign off at this point so that you make sure you get this right. This is the exact same principle we have for the starter relay. It's exactly how it's going to work, which we're going to go over here in a bit. But make sure you get this part down first. Get your sign off and then move on.
So with the basic principles of relays down, using the magnet to switch off and control the relay, what we can do now is we move on to the basics of electric motors. So this is going to be electric motors, not to be confused with Tesla motors. And this is going to be how our basic electric motors work. I was going to say DC motors, but this is pretty universal. So what I'm going to do is I'm going to go through here. You'll have this part of this graph on page 11. I'm going to show you how this kind of works out. So what we're looking at here, our key points of interest are the poles. So the center magnet right here, where it's red, that I have drawn right there, that means that it's staked. That means that that magnet is fixed. It's got a dowel, a metal rod that runs through it. It can rotate on that dowel, but it's not going anywhere else. The magnets on the ends right here are fixed, so they are bolted into place and they don't rotate at all. So we just strap them into a casing, a housing, whatever, and they stay. They don't rotate at all. If we look at the poles, so we see the south poles here, and then we should see the north poles right there. So north and north, south and south. Going over simple principles of north and south attraction, that means that the south pole is going to drive away the other south pole. So if we look at the bottom magnet here, so if we look at the south pole, that means that this magnetic flux line is pushing away on that end right there. That also means that on the top magnet, the North Pole is pushing away the North Pole. And since the top and bottom magnets are affixed, they're not going anywhere, that means the only choice for something to eat that energy is for the center magnet. And what it's going to do is it's going to rotate. So it's going to rotate away because the two north ends are pushing away from each other and the two south ends are pushing away from each other. So you see these lines, these rotation lines, showing that that's the direction that they're going to rotate in. So it's going to rotate away. So that's what we want this to do. Once it starts to rotate enough, we hit the second part. So it's going to rotate until we start to get better attraction. So now that we see on here that this is a south pole and this is a north pole, and this is a south pole and this is a north pole, which means they want to pull towards each other. So that means the north and south are getting dragged together, and it means the south and north up here getting dragged together as well. So that's what we want them to do. So we want them to rotate until it lines up. In a perfect world, once it reaches straight up and down, and this block is flat with the ones next to it like this, that means it should stay there because the south and the north are going to pull into each other, and it's just going to stay static right there. So what's happening is it's getting pulled in, and we see the rotation lines. Here's the trick, though. Notice that we have windings. We have the copper windings around the fixed magnets. And what's going to happen is before we reach this parallel section right here, we're going to switch the polarities of the magnets. So if you look on the previous picture, so here I am, here's figure B. You should notice, and let me get all my junk out of the way there. Let's clean this image up. Yeah, that's pretty. Like magic. So if you look at the poles on this one, this bottom magnet has a south pole, and this top one has a north pole. Once we switch the polarity, which means what? Which means we're going to change the way that the power goes through. If this is positive and this is negative, this is positive and this is negative, on the next page, notice how the poles switch. So now what we have instead is this switched to a north, this switched to a south. South and north, north and south. And that's because we're going to switch where the current goes through on the magnet. And if we change that, we change the polarity of the permanent magnet. Now we're at the same place we started at, which means that we have the north end right here, which is now pushing against the north end of our rotating magnet. The south end is now pushing against the south end of the magnet. And that's going to cause it to rotate until this south end starts to match up here, and this north end starts to mount up here. Then we get this picture again. And then when we're done, we just rotate it all. There they all are together. There's our 3 steps. So if we look at the first one, right here, we see north and north driving each other away, south and south driving each other away. On the second set, part B, we see that they're getting a little bit closer. The south is pulling up to the north right here. North is pulling up to the south pole right there. They're almost in line. They're almost perpendicular with each other. Almost. But right before that happens, we're going to change the polarities. The momentum of the center magnet is going to flow through that point of polarity, and then we switch the poles of the magnet, and we do it again. And the idea is we just do this again and again and again and again. And this is how we can get 2 sets of magnets to drive a single magnet. And again, as we talked about the different layers to increase magnetic force, if we increase the amount of voltage that goes through the fixed magnets, so if we increase the magnetic force that flows through the fixed coils 1 and 2, so let's say if you look on the far left over here, that we change this from 5 volts, so each magnet gets 5 volts, and by the time we switch to the next one, we change it to 10 volts. So we got 10 volts here and here, so there's a doubling of the voltage. That also means that these magnets are going to get even stronger, which means they're going to push even harder on the center magnet, which is fantastic because that's going to drive the center magnet even harder, which is going to create more torque. It's also going to cause the speed to pick up a little bit. So the center magnet's going to rotate faster and it's going to make more power. This is how we create electric motors. If I increase the number of magnets that sit around, so instead of having coil 1 and coil 2, I have coil 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 on the outsides, I create more coils, and if I send more voltage to them and I increase their coil windings, I can make this electric motor incredibly strong. This is how Tesla manages to build cars that create so much power. This is how they get their 12-second quarter mile, 11-second quarter mile, 4-second 0 to 60 times out of just an electric car. They have a center magnet set and they have an insane number of exterior magnets, and they just put a boatload of power to them. The only trick is that we have to remember that this needs to switch polarities. We need to switch before they become perpendicular. And as long as we can cause that switch, we can make this thing rotate infinitely, and we can create a lot of power. We just keep it going. Switch every time the poles start to match up. Once we get north and south and north to come together, we just switch them up, and then it drives again. Switch, drive again. Switch, drive again. So what I brought up on screen here is I brought up a general field winding, which is more realistic to what we're going to use as a starter. So we're building up slow. We're taking our baby steps up. What I'm going to do is I'm going to explain this. So if you look, this would be in our previous example, here's coil 1, and here's coil 2. So that's what the north and south magnets are right there. The center one is obviously going to be our center magnet. So that's the one we were talking about before, the one that we rotated around. Now what's happening is we're sending power to change the phase of the center winding. And what that means is we have this piece called a commutator. And what happens is this is basically north and south right there. And what's going to happen is as the power comes in, we're going to rotate this piece in the center. And every time we reach a 180-degree half turn, that's what's going to switch the polarity of the centerpiece to cause it to keep turning. So what's going to happen right now is I had to dig super hard into the archives, and boy howdy, let me tell you, you're going to like this. I'm going to give you guys a short video. It's going to show you how this commutator works. It's going to explain how this is happening. Before you start, make sure that you have the magnetic picture I brought up with figures A, B, and C with coil 1 and 2 and follow along. Watch how it mimics the same concept here in the video.
Now, if we already have the magnetic field and the current, let's see what happens. Here's the magnetic field and here's the conductor, which is a very simplified armature, just a loop of wire connected to a battery. When we turn on the current, we have movement. The conductor is moved. The reason for this becomes clear when we examine the characteristics of magnets a little more closely. Every magnet has a north pole and a south pole. Unlike poles of magnets attract each other, whereas like poles repel each other. That is to say, if the north pole of one magnet is placed near the south pole of another, the attraction is so strong that they move closer together until they touch. Let us take a screen and place it over the magnet. Then sprinkle it with iron filings. Notice the pattern of the magnetic field that forms around each magnet, and the concentration of filings between the unlike poles. But if like poles are placed together, north against north, or south against south, the magnets are pushed away or repelled from each other. Now, when a conductor is formed into a loop and current flows through it, the loop itself becomes in effect a magnet and is known as an electromagnet. With the aid of iron filings, we are now able to see the pattern of the magnetic field. Like all other magnets, this one also has a north and south pole. Which is the north and which is the south is determined by the direction of the current. So, if we change the direction of the current, the poles automatically change positions. This is going to be the north pole of the loop as soon as current begins to flow. When we place the north pole of the wire loop near the north pole of the bar magnet and turn on the current, the loop starts to rotate because its north pole is repelled by the north pole of the bar magnet. At the same time, similar repulsion is taking place at the south poles. Actually, the repulsion of the poles ceases at this point and the attraction begins. The south pole of the magnet attracts the north pole of the loop, and the south pole of the loop attracts the north pole of the magnet. And so the loop's north side continues to move in order to get as close as possible to its objective. Just before becoming aligned, the current through the loop is cut off. Momentum carries the loop a little past the magnet's south pole, and direction of the current through the loop is changed. Notice the loop rotate another half turn. That's because its polarity has been changed. The side of the loop that was a north pole is now a south pole and vice versa. Here again the repulsion and attraction is repeated. The power of this repulsion and attraction is doubled because it is taking place at both poles at the same time. Therefore, if it were possible to keep changing the direction of the current at precisely the right moment, the loop would rotate without halting. This is the job that is done by the segments and brushes. The segments are made of copper, which is an excellent conductor of electricity. Each segment forms a half circle and is connected to one side of the loop. The segments rotate with the wire loop. These are the brushes. They remain stationary while the wire loop and segments rotate. Every time the loop rotates a half turn, each segment disconnects from one brush and connects with the other. The brushes are wired to the source of electric power, the battery. When the switch is on, current always enters the wire loop through this brush, then returns to the battery via this brush. Let's see how it works out. As soon as current starts to flow through the wire loop, it becomes an electromagnet with a north pole and a south pole. As we have already mentioned, the north pole of the loop tries to get as close as possible to the south pole of the bar magnet. Just before the loop becomes aligned, each segment disconnects from one brush, momentum carries the loop past its objective, and the segments connect with another brush. This changes the direction of the current in the wire loop, which in turn changes the loop's polarity. The loop's south pole becomes the north pole. As such, it rotates toward its opposite, the south pole of the bar magnet. But again, the direction of the current in the loop is reversed. So the north pole of the loop and the south pole of the magnet never quite get together, and the rotary movement continues as long as current is flowing. In this way, the starting motor changes electrical energy, as represented by the flow of current, into mechanical energy, as represented by the rotation of the wire loop. However, since a single wire loop will not develop enough power to be of any consequence, many loops or windings are required. Each winding must have its own pair of segments. Now, if we space these windings around an iron core, we have what is called an armature. The actual connections and arrangements of the windings are such as to allow a maximum amount of current to flow through the armature coils when they are in their proper relationship to the pole pieces. This allows each winding to add its turning effort to the others, so that they all work together to rotate the armature, as the complete assembly is called. Here we see the armature in a magnetic field composed of 4 bar magnets, which increases the lines of force of the magnetic field for the considerable power required. However, these larger magnets, which increase the rotating power of the armature, are too unwieldy. So, like the generator, pole pieces rather than bar magnets are used for the starting motor. These pole pieces have conductors wound around them. When current flows through, it builds up the magnetic field and the attraction of the poles is sharply increased.
Yeah, you like that, huh? How's that for some super retro stuff right there? Yeah, that's out of a U.S. Army training video way back in the 60s. It's pretty good stuff. I hope it makes a little bit of sense, because what's going to happen is we're going to use that armature and commutator bar concept as we move forward and talk about the entire starter itself. So what I'm going to have you do is I'm going to have you pop open the section in your packet, and we're going to go to about page 13. You should see a picture of a starter in its blown apart pieces. Look upon the automotive starter, ye mighty in despair. So that's what we're going to do, and I'm going to burn through these sections on the board here real quick, and then I'm going to show you them in person. So if you look on the first page, the first piece that I go over is the pole shoes. So the pole shoes are the fixed magnets, and they're mounted inside the body of the starter housing, and they have coil windings wrapped around them to increase the strength of the starter when they go up. If you look at your ABC example of the rotating magnets, these are the coils. So this would be coil 1, 2, 3, and 4. So when I show you the example in real life here real quick, these are going to be those coils. These are the fixed magnets that do not rotate. They too have windings around them so that when we send power into the starter, they get stronger. That's what the pole shoes are. If you turn to page 14, the second one that I have is the armature. So the armature is the rotating magnet from our previous example. So this is going to be the rotating center magnet. So that's the one that's going to rotate. So this device slides inside the body of the starter. It gets suspended on both ends by bushings. So it gets held up so that it can turn. So unlike the example I gave you before, this armature is not one magnet, but it's many. And I'll show you this in the example coming up here, but they're broken into slatted sections. This allows more power to be transmitted through the motor, and it smooths out the action. This is sort of like the difference between having a single cylinder engine, like on a single piston motorcycle, and having 8 cylinders, like on a V8 car. So the more armature bars that we have, the smoother the operation is and the more power that we make. So the third one I give you down there at the bottom is the commutator. So the commutator sends the power to the coils and the armature. So it gets fed by carbon brushes, which I'll show you here right quick, and this is what feeds the power in. So the commutator sections are also split and divided. Every time you see a split in the commutator section, you're changing the polarity of the magnet. So what's happening, as I mentioned before in the ABC example with the 2 coils from previously, is that at certain points we need to switch the polarity. Otherwise, the center magnet won't keep turning. That's the purpose of the commutator. It's going to keep splitting at so many degrees of rotation the polarity of the entire magnetic set inside the starter so that it keeps turning and keeps generating torque. Without the commutator, we would rotate and then just stop because we wouldn't get any switching of the polarity. Number 4, if you turn your page, you should have the solenoid. Another name for the solenoid is just the relay. So this is the starter relay. So we gone over relays. You set one up, you clicked it over, and I pray to God you got the signature for doing so. But it's the exact same concept as the tiny relay that you work with. Same one. It's just a bigger relay because it has to deal with a lot more current. So the small one that we had you guys wire up and work with is a small relay designed to handle a couple amps. The big fat relay that's actually mounted to a starter has to be able to handle 200 to 300 amps depending on the application. So it's the same thing. It's just a lot bigger. Also what happens, and I'm going to show you here real quick again, is that the solenoid drives the pinion gear, which is attached to the armature, so that it engages with the flywheel and turns it. So that's what we're looking for in that case. And so if the solenoid fails, sometimes we can't get the drive gear to engage. And the last one is the drive gear. And this is what engages the engine. So typically this engages the flywheel, or if you have an automatic transmission, it engages the flex plate, being pedantic with our terms. But this is just the gear tooth that gets driven forward and is attached to the armature. So the armature is the piece that turns, so we attach this drive gear to it, so as the armature turns because of magnetic force, it transmits that power into the engine. And that's what's going to cause this baby to start up. It does have on it what we call an overrunning or locking clutch, so that way it drives forward and locks in one direction, but the moment you turn it in the opposite direction, that thing is going to push back. It's going to reseat away from the flywheel or the flex plate so that it doesn't stay engaged. If you didn't have a return spring and an overrunning mechanism, you would push the gear forward, it would engage the flywheel, and then once you cut the power to the solenoid, it would just stay there. And that would cause the armature to turn at engine speed and pretty much blow up the starter. This is not unheard of. Sometimes they stick and then it blows the starter up. It is a not common problem, but it does occur. But that is why we have the drive gear, and we have a one-way clutch on that as well. So let me go through the operations, or I should say the internals of the DC starter motor here. I'm going to show you in person.
All right, so let's go over our actual physical starter itself. I'm going to give you my example right here. So there it is in all of its glory. So we have the starter and the body fully assembled here. And this is our relay sitting right there at the top. So again, most starters are going to have the relay attached to it. Some older Fords, for example, have this relay disconnected from the starter itself, but they're usually one unit. We have our inputs there, relay, body on top. You can see on the inside our pinion drive gear sitting right inside there. So I'm going to take and give you a pulled apart version of the body. So what's going to happen is if we take the starter right here and we take the cone piece off, then this is what we're going to see disconnected from it. So if we take the cone piece off, we can see the drive pinion gear on the inside. It's got a little clutch throw, so we can attach right there. If you look on the inside, we're going to pull this apart. We can see the pull shoes. And on the back, we can see attached to the commutator bars. So we got our commutator bar sitting right there, which is attached to the armature on the inside. So as you talk about the brushes, you can get in there and see those sitting right here against the commutator, and that's the commutator sections, those tiny little indentations. And the brushes are what's feeding the power in to power up the magnets, and as it rotates, you can see the brushes rub across there. What's happening when this starter starts to die out is these brushes sometimes start to wear down. So if the brushes wear down, they're not going to touch the commutator very well. We're not going to get enough power. We can also sometimes get them to stick. There are inside here tiny little springs that push the brushes in, and sometimes the brushes will stick, and that's why sometimes when we jam on the starter and hit it, it jostles these loose and gets them to sit on the commutator again, which allows it to rotate. If you look at the pinion gear, this is our one-way clutch. So this is our clutch. So we have a fork that's going to slide into here. When we turn it on, it's going to engage the pinion gear with the flywheel, and then it's just going to turn. Once it starts, this is going to rotate backwards, and the pinion gear is going to reset. So engage, disengage. That way we engage it, start, start, starts. We kill power to it. The clutch is going to pull it back, and that way it disengages from the flywheel. If this sticks, it's just going to overrun. It's going to cause the starter to keep turning, so we got to disengage it right there. If we pull these bits and pieces apart, so we can pull this out, And this is our section of our armature. So we sit here and we have our armature with the segments on it. There's our commutator right there. And this is the pieces all in one bit. You can see the windings to help field the magnet so that it turns. Inside the body of the starter itself, you can see the pole shoes, those little red bits and pieces right inside here. So we should be able to see the pole shoes inside. Those are also part of the magnetic setup that we talk about. You see the windings around here? That's also what the commutator bar is going to feed. There's as the brush is all pulled apart, dangling all loose. But this is what it looks like on the inside of the body. So we have these permanent magnets. Another reason that we don't actually hit the starters to get them to work right is if you hit it too hard, you're going to split these magnets in half, and then they're just going to break. If these magnets break or you drop this like that, you might just break the actual pole shoes inside of there. So be careful not to do that. What we have next, so I'm going to set up here, is the relay. So again, I talked about pulling the cone section off right here. That's what the cone section looks like disassembled, where the housing is. So you have the relay attached right there, and that's where our clutch yoke is at. So that's the yoke that's going to engage the pinion drive. So when we power it, this is going to pull back. So it's going to take this, there's a magnet here, it's going to pull back, and that's going to cause this to drive forward and engage to the actual pinion. When we take power away from the relay, it releases, and you can see there's a spring in there. So if we pull this apart, hopefully I don't drop it, clumsy hands. So if we take this apart, we see the actual yoke inside there, and this is the relay itself. This is a permanent magnet in the back. It's got its inputs and its outputs. If we take a look here, this is what we have. We have the return spring, and then we have the drive gear itself here. Notice how it's fixed right there. So what's going to happen is when we power up the relay, this metal piece is going to get pulled back, and that's what's going to drive the pinion forward. When we actually kill the power to the relay, the return spring seats it back in place. So that's how that's going to work. That's the purpose of this relay right here, is this big magnet powers up, and it's going to take it, and it's going to pull back, and that's what's going to engage those forks. So those are physical bits and pieces of our starter assembly. So talking about the starter relay itself, if we look at mine on this example I have, this one's broken. So I'm going to give you a better example here soon enough. But you'll notice that we have the S terminal, the R terminal. There's a nut right here that attaches to this strip. So this is what feeds in right there. And there's a terminal broken off here in the top. So I'm going to switch this real quick. I'm going to keep that right there. I'm going to give you my pull away. So again, this is the same one, S terminal, R terminal. This is the strip that's going to go down to the starter, and this is the power in jam nut. So we talked about relays a lot. This is basically going to be the control side of the relay, and this is the power side. You know, we had the 30 to 87. So what's going to happen is the S terminal gets a tiny wire put into it. That's what's going to the starter, the ignition switch. So when we turn the ignition switch, we're going to feed power into the S terminal right here, and this gets grounded out through the body of the actual relay, because this is mounted to the starter, which is mounted to the block, and the block itself is mounted to the ground. So we send power in here. Once we feed it through the switch, turn the ignition switch on, power comes in, it's going to go back to the battery, and that's going to engage this relay, which will then connect this terminal to this terminal. So we have power come in and go out, which is going to end up sending power into the stud that would be at the top to this stud right here, which sends it into the starter. So it powers up the commutator, so that way we can spin the armature. That will then engage the pinion, because it's going to pull back. It's going to pull and engage it. So again, the relay is just an S terminal. It comes from the ignition switch, which is going to break the connection. It's going to close the connection from power in down to here. Starter goes. Simple. The relays are just the same. Relays aren't going to change. Control side, power side.
Okay, so with the actual operation of the starter, how the commutator bar works, how it's going to turn, how it's going to engage the starter, we're going to finally jump into the big kid territory, we're going to go into how the actual circuit works and how to diagnose the circuit. So right now I have a really simplified picture. You can tell by all the bright childlike colors on screen that it's made to be real easy. But that's literally what the starter circuit's going to look like. So we start out, we have ourselves our battery sitting right there. Source of all power. So everything starts from the battery. You see that we have the positive and the negative. Again, just like in station 1, this is our ground connection right there, which means that any point that shares that symbol means that they are all connected back to that point. That's what that means right there. So make sure we know what our ground connections are before we continue. So in simple operation, we have the battery. Battery's going to feed power to the starter relay, and then it's also going to feed power to the ignition switch. The ignition switch controls the control side of the solenoid, which is just our relay. So once we close the contacts of the ignition switch, we will then get power to go to the starter solenoid / relay, which will then connect power to go through the relay to the starter motor. So that's how that's going to work. So once we close the ignition switch, we're closing the contacts on the control side of the relay, which is going to close the relay and allow power to flow from the battery to the starter. So make sure we got that simple and easy, clear right there. Once we have that, power is going to flow through the solenoid to the starter. It's going to flow through the starter, cause the starter to turn, goes to ground, comes back to the battery. And you know what? That's it. That's how simple the starter circuit is. It is literally that easy. It breaks into two parts. Control side, which is again controlled by the relay. To turn the relay on, we just have to close the contacts of the ignition switch. That's where you put the key in and turn it, or if you're push button start, you push the push button, which will close the contacts of the starter solenoid, allowing power to flow from the battery through the starter motor back to the battery. And as long as the ignition switch is held closed, the starter will receive power. The moment you let go and turn the key back to its run or stop position, you will cut the power to the solenoid. It'll break the contacts, and it is that easy. No joke. That simple is how easy this circuit is. I'll give you another example with another diagram. This one's a little more complicated. This is more formalized. It looks like the kind of diagram we're going to see in a service manual. The picture is going to be a little different. Notice that we have the battery again here, and that we have the ground connection right there. So these descending bars that look like this just means ground. That means any point where you see this, they are all connected to one another. That's what that means. So get used to seeing the ground connection, and that denotes that our grounds are connected to one another. We have the positive side of the battery right there, so that's where power is going to start. Notice that the battery feeds power to the ignition switch in start position right here. But we also have a new item that I've added, which is the park neutral safety switch. So this is present on all vehicles, particularly this is going to be specific to an automatic. And this is a switch that will stop the starter relay from engaging unless the car is in park or neutral. So any vehicle that you deal with, if it's an automatic, is going to have a park neutral safety switch. The inverse of this for a manual transmission is a clutch safety switch, which means if you don't press the clutch down to disengage the clutch, you will not be able to complete the circuit to kick on the starter relay. So not only do we have an ignition switch, we have an extra layer of safety, which is the park neutral safety switch. So just be aware that that's what that new item is. So in this case, to get the relay to kick on, which is this device right there, we need to have the vehicle in park so that we close the contacts of the park neutral safety switch, and then we turn the key. And once we do that, power comes all the way up, goes through the coil, which again magnetizes to pull the switch closed here and connect this. And the power is going to go through the ground, and it's just going to go back to the battery. So that's the control side of the circuit. Same concept of what we just talked about in the previous picture. The only difference is I've added a park neutral safety switch. If you're in park, this contact will close. Once you turn the key, this contact will close. Power comes through, up, through the coil, to the ground, and heads back. That will close the connection here. That's what the control side's doing. The power side, of the starter circuit is just as simple. Once the control side is engaged, power flows up through here. It's going to go through the power side of the relay, which again is closed, assuming we've turned the key and we're in park. Comes through high current, 150, 200 amps. Comes through the starter motor, which is this right here, M1, which means motor 1. It's going to go through the motor, cause it to turn. Power flows through to the ground, and since the ground connection means they're connected, it's going to come all the way back to the ground and return up to the battery. So long as you stay in park and you keep the key turned, power will continue to flow to this starter. Once you turn the ignition switch off or you jiggle the actual shifter and take it out of park or neutral, you will kill the control side of the circuit and cause the power side to lose its power, and then the motor itself will shut down. That's how simple this circuit is in operation. So right now, this should make at least a pretty decent amount of sense to you. If you've run through station 1, you should really kind of have a grasp of this. If you're not understanding how this circuit operates in principle, what's the ignition switch doing, what's the park neutral safety switch doing, how does the relay work, you need to stop, you need to go back, you need to watch the section I shot on the relay, make sure that makes sense to you, or you need to get some help. Because we're going to use this model, this picture right here, for all of our diagnosis. And if you don't understand how the basics of this work, the diagnosis is going to fry your brain, man. So make sure that this makes sense before you continue on. Do what you got to do and get some help, but you should understand the basics of this circuit, control side and power side. It's not too much, shouldn't be too complicated, but if you need some help, go get it. Okay, so what we're going to do now is we're going to go into the 3 steps of starter diagnosis. So I will shorthand as starter diag. Like Stregonona, starter diag. Starter diag breaks into 3 parts. 1, and this is the most important. This is battery check. I'll go over a bit of detail on the battery check quick, but we're going to do part 2. So the battery check, and then we're going to do, I'm going to erase that. I'm going to do check the power side, and then we're going to do check the ground side. These are the 3 steps to starter diagnostics. Check the battery, check the power side of the starter, and check the ground. These are our 3 steps. There's only 3. It's only 3. It's that easy. It's not a lot. It's not a whole lot. Don't get crazy. Don't get confused. Just 3. Check the battery, check the power, check the ground. I'm going to show you how to do all of these right quick. So let me go ahead and clean off my board. There we go. Nice and clean. So starter diag, step 1 is battery check. So we're going to go over that first. As I mentioned, the paperwork should be around page 18. The battery is the alpha and the omega. It's the beginning and the end of all circuits. If there is a problem with the battery, the starter circuit's not going to work right. Any problem that crops up in the battery will cause so many issues across the entire car. So most people jump past the battery and their drive to just get in there like a mad dog and start diagging, but do not skip the battery. Problems with the battery equals problems with every other electrical system on the car. So the easiest thing to do first is we're going to check open voltage, open source voltage. So open source voltage is what we're looking at here. In this case, if you've been through the battery station, that's good. You should know about this. If not, we should be able to hook a voltmeter up, and we should get 12.4 to 12.6 volts. That's the first thing we're looking for here. If you have 12.4 to 12.6 volts, chances are pretty good that you should be fine to continue your diagnostics. As we cover in the battery section, which I pray to God you did before you did this one, but if not, we'll fill you in. Open source voltage tells us what the potential of the battery is to supply power to the rest of the circuit. This is just with a voltmeter attached across the top of the terminals. So we have a voltmeter sitting right here. Here's my connection, positive and negative. I touch this, and the screen should, with any luck, read 12.6 volts. If it reads this, we're generally good to go. As covered in the battery section, just because it reads 12.4 doesn't mean it's perfect. We need to do a conductance test on the battery. We need to load test it to guarantee that the battery isn't crippled, and that when we actually run a like a current through it, or we try to load it, that isn't just going to collapse on us. But, to be fair, if you can read this as the voltmeter and you see 12.4, 12.6, chances are pretty good the battery's not bad. However, do a conductance test first, and the conductance test should read 12.4 to 12.6 volts and should tell you that the battery is healthy. If you have that, step one for your battery check is done. So, next step on a battery check, and this seems redundant. Check the connections themselves. This would be the connections I'm going to show you on screen right here. These are going to be the connections right here. So when you wiggle them around, these suckers should be tight, man. They shouldn't be loose. The cable shouldn't be coming off. They find through a handful of studies that about like 30% of your failure to start problems, which is people turn the key and the starter doesn't go, are caused by loose connections. If the terminals attached to the cables are not tight, you can't get power to go through them. You're going to have a sliver of metal contacting metal, and it needs to carry 200 amps. Just isn't going to happen, man. Check the loose connections. Check the power, check the ground, check the cables. If I walk over and you tell me, oh, Mr. Webb, car doesn't start, the first thing I'm going to do before I even pull out a voltmeter is I'm going to reach my grimy hands down. I'm going to twist those terminals. And I bet you 30% of the time, they're going to shake loose. I'm going to look at you with a stern look. I might shake my head. I might squeeze the temple of my eyes, faking a migraine and frustration. And that's going to tell you that, hey, man, better check these cables yourself. There should be no reason you don't check the cables. When you walk past it, check the cables. Treat it like it's your baby, man. Walk by, you want to feed it a bottle, you want to touch it, you want to coo at it. That's what the terminals are. They're your sweet, sweet baby, and you want to pay attention to them as much as you can. Don't neglect them. They're going to grow up to be big, strong battery cables one day, and the only way they could do that is if you pay attention to them. So, in summary, check the cables, check the connections. Do not overlook them. They are very important. So now we're going to do part two. So we checked the battery, terminal's good, we've load tested it, connections are tight, our bouncing baby battery connections are doing just fine. We're going to do the power check. So before I jump in and do the power check, sounds a bit like Gorbachev, I don't know why I sound Russian today. What we're going to do first is I'm going to run you through, once again, how to do a basic voltage drop test, okay? So here we go. There's a 2 ohm resistor, there's my 12 volts. Oh man, it's looking like station 1 all over again. I can feel you sweating it. Feel you sweating it right there. There's 12 volts, 2 ohms of resistance, 6 amps. Ohm's law is a beautiful thing. So that's how we're going to find that. It should be a 6 amp circuit. I'm going to go over the voltage drop. So what the meter is doing, if you have not had the luxury of actually taking the DVOM course yet, which we do for diagnostics, by the time I wrote this, it was station 8. It might be a different station right now. And I wrote in your syllabus that I encourage you to take the voltage drop course before you take this one. I hope you took that advice. But if not, I'm going to run you through it. So when we hook up a voltmeter, we have positive and negative connectors. And we set it to the volt scale. The voltmeter itself is a meter that shows difference in voltage. So when we look at this circuit, and I hope to God you remember this from station 1, we have 12 volts, and we should have 12 volts travel up. So 12, 12, 12, 12, there should be 12 volts here. Once the voltage pushes through the resistor, there should be 0 volts, 0, 0, 0, 0, all the way back. Because Kirchhoff's voltage law says voltage goes in and doesn't come out. I've used this simple circuit with 1 resistor in it because if it's the only resistor in the circuit, all the voltage should drop going through it. There's 1 load, all the voltage should travel hard up to it, go through it, and then disappear. That's a fundamental of circuit design. That's how the physics works. That's a guaranteed happening. It's going to happen just like you throw objects up, they come back down unless you're standing up in space station. So be aware that that's how it works. So because of this, the voltmeter is designed to show us differences in connections. The positive post, if we touch it here, I'm actually going to change the color because color is important. I'm going to change my positive right there. What the connection is going to do is it's going to sample 12 volts. I'm going to draw my ground as green, because ground is green, easy to remember. So we're going to run it up here right there. So there it is. So there's green. The green should also sample 12 volts. Why do I say it samples 12 volts? Because that's my source voltage, and it should be 12, 12, 12 all the way through that wire. I pray to God once again that makes sense to you. So if we sample 12 and 12 on these two connections, the meter's job is to take the first reading, which it goes, whatever the first reading is, it will always subtract it from the second reading, which in this case is 12. So that means that this meter should read 0 volts on the screen, because a voltmeter is designed to show you the difference in voltage between two test points. It says the difference between point A and point B is 0 volts. There is no difference. If there is no difference, that means there is no drop in voltage. If there is no drop in voltage, that means there is no resistance between point A and point B, which is good, which is very good. It's exactly what we want. That's what's going to tell you. No difference in voltage means no resistance in that line. That is exactly what we are looking for. So, what happens if we take the leads and set them on the other side? Take my red, I'm going to set it right there. This should sample, once again, 12 volts. I'm going to take my green, because green is ground, sing a little song about it. It's going to go up on this side. Now it is on the other side of the resistor. That means that the voltage should have dropped going through that resistor, which means the green test lead is going to sample 0 volts. So that means in my equation on the bottom, the meter is going to take first probe, which should read 12 volts. It will subtract it from the second one, which is 0 volts, which should then give me, God, I hope you guys remember your arithmetic from, second grade, and it should give you 12 volts. Because 12 minus 0 is still 12, which means the meter will read 12 volts. And what this tells you is the difference between point A and point B is 12 volts. So that means between this point, from here all the way over to here, we have lost 12 volts, which is what we should lose by design. But the purpose of this is to show you what the actual meter is doing, to show you why we get the readings on the meter. It doesn't mean that when I touch point A and point B, there's 12 volts there. No, it means the difference between point A and point B is 12 volts, which is an important distinction, very important to realize. So what does that do for us in terms of diagnostics? So we're going to do this again. So as we have established a million times, and I will repeat a million times until the entire world understands, we have 12 volts here, and we should get, because there is no defined, I have not drawn in this wire any resistance, we should get 12 volts up to here. So let's say we do our voltage drop test again. So I draw my red wire right there. I'll take my green wire. Not going to sing it this time because I'm going to pay you guys for that luxury now. Once you become popular at Cavalry, you got to pay. You have a green wire that heads up here. So let's draw this, and let's assume now that the meter shows not 0, but shows 1 volt. So without telling you what the sample is right here or right there, we can make some assumptions right here. This is telling me, as a technician, that from point A, which is right here, to point B, I have lost 1 volt. So I have a loss of 1 volt from point A to point B. I have not drawn any resistance in this circuit, so I should not lose that 1 volt. What I can assume right now is that between A and B there's some type of resistance. Where is it? I don't exactly know, but I know that it's there, and it shouldn't be eating up my 1 volt. The reason this happens is because this is sampling 12, and the green wire is now sampling 11 volts. And somewhere in between the two, somewhere in here, is resistance. There's some resistance in there, and that's a problem for us. So what we can do in this case is if I redraw my lines, I can keep my red where it's at, but I can move my ground wire, my green wire, and I can move it a little bit closer. So I can draw it right there. My meter still reads 1 volt. That means, again, somewhere in here is the resistance. So I need to keep moving it a little farther back. Yes, I do. Yes, I do. And that's what I'm going to do. So move it right there. Now it reads 0 volts. So when the green was sitting right here, this meter read 1 volt. Once I move this connection here, it read 0 volts. Now I'm narrowing down where the resistance is at. That's if I want to be that specific to find where the resistance is at. But I hope that shows how you can move the test leads around to isolate where the resistance is at. The big takeaway again is, what is the meter actually doing? My only concern for you, though, and this is where your diagnostics will stop for the most part, is that if I touch this right there, and I get this reading, so I get 1 volt on my meter, assuming that I walk up to this board and I check a connection right there and I go, oh, that connection's tight, it's not loose, and I check this connection right here and go, that's tight and it's not loose, the resistance has to be somewhere in this wire. What do? I take a big set of cable cutters and I cut the dang thing out of there and I just replace it. That's it. I don't care where in the wire that sucker's at. I'm just going to cut that thing out and replace it. That's it. You don't need to get so pedantic as to chase the resistance down, so long as you check the connections and make sure they're tight. Remember, it's important to check our little baby connections. And once those are good, who cares? That means there's too much resistance in that wire, we get rid of it. That's all that we do. The same thing can happen on the ground side. So if I take this lead here, I touch it right there, and I take my ground lead and I touch it right there, and I should get 0 volts. There should be no difference from point A to point B, because I haven't drawn any resistance in there. Should be no resistance. But if my meter does read 1 volt, that means there is some resistance in this wire. Again, assuming that we check these connections and they're tight. If the connections are good and we still get 1 volt lost in that wire, we're going to take it. And we're just going to replace. That's it. I don't care where in the wire it's at. I'm too lazy. They don't pay me to do that. I'm just going to cut the wire out and replace it. That's what we're going to do in this case. Now, you ready? You ready for a little magic trick? Let me show you how this all relates to what we're doing. Watch it. It's going to be magic. It's like a sleight of hand. You can't see me dancing around right now, but I am. I'm excited. So here's the magic trick. There goes that resistor. I'm going to draw an M right there. What? What? Is it popping up yet? Holy smokers, look at that. This is, in fact, a circuit for the starter motor. That's it. If you remember from the control side on my starter motor, all that thing is, from here through the relay to this motor, is literally this picture right there. Assuming there's a relay, but I've cut that out for simplicity's sakes. That's it. That's all we're doing. So when I say we check the power side, what I'm telling you is we're going to check from the battery right there to the point on the motor where the power goes into the starter motor. And I should see very little to no voltage drop. And if I do, that means that this is okay. That's what that means. That's what we're doing for a power check. That's what we're going to do. So let me give you a more detailed picture on this. So here's my same diagram as before, and I've drawn in my voltmeter. So my voltmeter's right there. I know it's a real pretty box, but I need to point it out that that's what my voltmeter is. What's happening is the same thing we just talked about on my simple diagram. I have a test point right there, and then I have a test point right here. Technically, I could draw this wire like, touching the motor right there, but the concept is the same. So one of our takeaways that I'm going to expect from you is need to know how to do a voltage drop. This is how we check the power side of the starter motor. What we're going to get is there should be no more than 0.3 volts dropped between the power cable through the relay to the power terminal on the starter. No more than 0.3. Your meter should be set to the 12 volt / 20 volt scale when you test this. And when we crank the motor over, so we attach to the positive terminal here and to the positive terminal there, when we turn the key, we shouldn't see more than 0.3 volts loss. If we see more than 0.3 volts loss, we have ourselves a problem. But we should not see more than that. If we see less than 0.3 volts, that means that this wire through this relay to this point is good. If there is less than 0.3 volts, that means that entire circuit, every wire in the relay attached to it with every connection is A-OK. That's it. That's all we have to do. That's all we have to do. I'm going to show you an example on one of our test vehicles here. So I'm going to show you right now live how we're going to do the positive side voltage drop. So this is just for the positive side to see if we get less than 0.3 volts. Let me show you. So with our meter set to 12 volts, we're going to hook positive to positive right here. And for the negative, we're going to hook that up to the starter. And the starter, of course, being reached underneath the car means that we have to drop that negative lead all the way down there. So you're going to want to drop it about where I'm showing you here, because that's going to give you enough space with the test leads that we have to be able to test. So once you drop it down like I have it, all the way down to the bottom, make sure you kind of wiggle it. If you get it wrong, you can always come back up and drop it again. I'm going to get underneath the car, and then we're going to go hook this up. So our negative lead is going to go onto the power wire, the big fat wire that feeds all the voltage into the starter, which you can see here with the arrow, and that's what you're going to want to connect it to. So I'm going to zoom in here. You can watch me, fumble around, try to get it connected. So make sure you get the alligator clip, right on there, and that way you're going to get a good connection. That way we're going to get a good reading. So then you come back up, you're going to start the car, watch for the voltage drop. Again, no more than 0.30 volts, and that's how we're going to voltage drop on the power side down to the starter. Fascinating, isn't it? Easy. Stupid easy test to do. And that's what we should get. So the question is, what happens if we get more than 0.3 volts? So imagine we do that test and the starter turns slow, or the reading sits there and it goes, no, you have 1.5 volts or 12 volts lost to that entire circuit. All right? So what we can do is we're going to go over the set. You should have on your paperwork page 20 where I've drawn out what do we expect if we get more than 0.3 volts. What can some of the causes be? So the first one that I have is too much resistance in the cables leading into or out of the relay and down to the starter motor. This is usually caused by corrosion or a poor connection. So that means too much resistance. For example, too much resistance in these wires right here. You might have bad connections at the battery terminal itself, but you shouldn't, because you checked it, right? And then make sure your baby's safe. But you might have too much resistance up here. You might have too much resistance through the relay itself, because this contact right here and here can wear down over time. Or you might have too much resistance in these wires that lead down to the starter. So that's the first one. Too much resistance in the cables leading into or out of the relay. As I said, the second one is a bad starter relay itself. So we can have a bad starter relay. So these contacts I mentioned might be bad. Or the starter relay on the control side might be bad. You see how it's got a winding right here? So it's got this nice winding coil. That coil can break. So the coil itself can break, it can separate and cause an open, or it too can get too much resistance, too much white chalky nonsense built up on the coil. That will stop the power side contact from closing. If that happens, we're going to have a huge voltage loss because power will go into the relay but will never exit out of it. The third example I have is a bad ignition switch. So the switch itself can go bad. So we have the ignition switch turn to the start position. If that switch goes bad, again, the key doesn't turn right, these contact points, which are heavy duty metal, can still wear down. And if those contacts don't close at all, the relay will not close the power side, and then we won't get any voltage through at all. We can also have a failed park neutral safety switch right there. Same problem. It's rare, but these contacts can wear out as well. So we can run into that problem too. The most common problem with the failed park neutral safety switch is user error, which means the car is not in park. So if you're turning the key and you're getting a huge voltage loss and you keep turning, nothing happens, double check to make sure that the shifter is in park or neutral. It seems laughable and it seems stupid, but it's common. It happens to me too, where I'm just like, why doesn't it start? Why doesn't it start? And I sit there and go, oh yeah, I should move it in park. Sometimes the contacts wear down on the park neutral safety switch and you just gotta jiggle it, man. Just take the handle and shake it around. If the park position doesn't work, turn it to neutral and see if that starts it. So we got park neutral safety problem. So we also have just a problem with an open or break in the wires that lead to the control side of the relay. So anything that causes like this wire to get too much resistance and break, or here, or here, or here, again, that's going to shut down the control side of the relay. If the control side of the relay never works, that means the power side is never going to work, okay? It's a very important distinction there. So the last tip I'm going to give you for the power side diagnosis is how much voltage is lost. So if we do a voltage drop, and we lose more than 0.3 volts, so let's say we lose 1 volt to 5 volts, all right? So we lose 1.1 to 5 volts loss. If this happens, chances are pretty good that there's too much resistance on the actual power side of the relay. So what's going to happen is you're going to get resistance on the power side of the circuit. So like here, it's going to be somewhere in here. That's what's going to cause. Again, this is a power side voltage drop only. So if you have 1 to 5 volts dropped or lost, chances are pretty good it's in the section that I just drew out in blue. If you have 11 to 12 volts loss, this is what we would consider a full loss. This is all voltage loss, period. Chances are pretty good that it is somewhere in the control side of the relay, or it's just a failed relay itself. The reason for that, I'm going to draw this in green. I hope this makes a little bit of sense here. You should have 12 volts up at this point. If the relay fails to close at all, either because the relay is bad or because the control side of the circuit with the ignition switch, park neutral, safety switch, etc. is bad, that means that these contacts never close and you will always get 0 volts on the other side. That would be your complete loss scenario, 12 volts loss. So if you do a power test, you do a voltage drop on the power side, you turn the key, you check your meter, and it reads 12 to 12.6 volts loss. Chances are pretty good that your problem is going to be on this section of the circuit, period. Not guaranteed, but I would go out on a limb and say about 95% of the time. So be aware of the voltage readings you get as well. 1 to 5 volts loss is either going to stop the starter from turning or make it turn slow. But if you get a huge loss, 12 to 12.6 volts, that means that that relay is never shutting at all. And why doesn't the relay shut? Could be a problem with the ignition switch, neutral safety switch, the relay itself, problem with the ground connection, something. But just be aware of the voltage loss that you're getting, so that way you're not chasing the entire circuit all the time. Make wise decisions with the information you are given. So that covered all the stuff we're going to do for a voltage drop on the power side. So what we're going to do next is shown on screen here. So we're going to do a voltage drop for the ground side. So this is the ground side of the circuit. You remember back to my basic circuit where we had the 2 ohm resistor I was talking about 15 minutes ago. This is just going to be the other side of the motor. So we need to check the ground connection as well, because the ground side carries just as much amperage as the power side does. Amperage goes in, amperage comes out. So if we're pumping 200 amps through the power side, we're going to pump 200 amps through the ground side. Again, amperage is movements of electrons that causes heat, which can cause resistance. If we have a bad ground connection, that's going to cause an open, and if you don't have a complete path back to the ground, the circuit will never flow in the first place. The power side can be immaculate, perfect, beautiful, like the Virgin Mary, and still not get the starter to move because we don't have a good ground connection. So it's important to ground test as well. So again, as you see here, we with one lead on the ground side of the battery and the other touching the metal body of the starter, we should get no more than, you guessed it, 0.3 volts drop while the engine is cranking. You have to load the circuit by getting the engine to try to crank over. The reason I say the metal body of the starter is that the starter's body itself, the casing, is always made of metal, and it's bolted to the engine. So that's what the ground is. There is no ground wire that comes off of the starter motor. It just grounds to the block, and the block is connected to the ground side of the battery. So there is no ground cable to touch. Just anywhere on the metal body of the starter is good enough. That's akin to touching the ground wire. And as you can see in the picture, I have my positive hooked up to the ground side of the battery, so that's going to be the negative post. So if you have your actual battery here, there's my positive, there's my negative. We're going to be attaching it to the negative post of the battery. So we're going to be doing that. And then I have the ground side of my voltmeter attached to the metal case. So we have the two connections right there. We should crank it over, and we should see less than 0.3 volts. That's going to tell me that between point A to point B, I have less than 0.3 volts lost. That's pretty good. That means there's not a lot of resistance in that connection, which is fantastic. We shouldn't have a lot of resistance on the ground side. We should not. So as before, I'm going to show you in person. So here we go. I'm going to pop you on screen right here, and I'm going to show you how we do the ground side voltage drop live on a vehicle. So I'm going to show you this, take a close look, ooh and ah at the amazing camera work. So we're checking the ground side. We're going to take the positive test lead and set it to the ground. So you're going to switch it over because we need to touch ground to ground. So you got that one there. You're going to crawl back under the car where your lead was at before, and this time it needs to touch the body of the starter. Now, you can press it against the starter yourself. You can attach the clip to this little outcropping right there. That's fine. I prefer to put it down here on this bolt because it tends to give you a better connection. It's stable, so I like to clip it right here. Either way, press it against the body or clip it to the bolt and you'll be set. And just like before, come back up and you're going to turn the key, start the car, watch the voltage drop, no more than 0.30, and you're set. That's how we do voltage drop for ground side. Pretty slick, huh? Not too hard to do. Same thing as the power side. We're just checking the other side. It's an easy test, it's fast, and it gives us really good readings. So what we're going to do again is the question, what happens if that side is not good? It's not good at all. So what happens if I have more than 0.3 volts lost? What could the potential problems be on the ground side that cause it to happen? On page 22 of your packet, I go over this. There's really just one simple answer. If you have more than 0.3 volts lost when you do the ground side voltage drop, you have a poor ground connection. This is typically caused by the starter either not being mounted properly to block, it's crooked, there's dirt between the mounting surface of the actual block and the bell housing, or the wire is coming off of the engine block, has too much resistance, it's broken, or it's loose. That's it. That's all it can be. There's no fancy relays or switches in the ground side. It's literally just a big chunky wire that carries current and then takes it back to the battery. That's all that we have. I'm going to show you a picture here on the board real quick. It's that one right there. So this is, when I say the ground wire, you see how absolutely close it is right there to the battery? It's this sucker right there. You notice how it has a bolt sitting right there. That is screwed into either the engine block or the frame of the car, because the whole frame of the car is simply made of steel. And the blocks are either made of aluminum or cast iron, which both conduct electricity, and we use the block or the frame to carry current. And then when it's all said and done, what connects the body or the engine to the actual vehicle is just going to be this strap. It's called a ground strap. That's going to carry it back to the negative terminal. You can have too much resistance in this wire, or there can be too much corrosion built up where that connection's at. So where that actual metal strap is, there might be corrosion behind there, there might be rust, somebody might have pulled it off and painted behind it. Paint does not conduct electricity very well. Or this bolt is loose. Because if that bolt's loose, you're not going to get that strip to push hard against the metal body, and it's going to struggle to carry current. Let me show you here live on the test vehicle that we have where the actual ground cables are, and you'll see how simple it is. You see how small that actual wire is. So that's what we have there. So if you have more than 0.3 volts lost, chances are pretty good that that connection's either loose or that cable's bad. And we can check that. Again, reach your hands down there, touch it, shake it around, make sure it's all good. So with all of that in mind, let's go back over our steps. So this is starter diag. Step 1, check the battery. Step 2, voltage drop, power side. Step 3, voltage drop, the ground side. So there's our 3 steps. As I have exhaustively detailed how to check the battery, how to voltage drop the power side, which is probably the most complicated, even though it's still relatively easy, and then number 3, voltage drop the ground side. What we get last then is our conclusions. So let's assume we did these tests. So we checked the battery, yeah, that baby's good. Voltage drop the power side, yeah, that's good. We voltage drop the ground side, yeah, that's good. So if you get a good battery, here's the stupid simplified version. 12.6 volts, you get less than 0.3 volts dropped, and you get less than 0.3 volts dropped on the ground side. Your conclusion, here it comes, you ready for this? The fanfare. Can you hear it? The crowds, they're cheering, they're cheering. Yeah, you can hear me slam that pen real hard. I'm super excited. It's a bad starter. That's it. That's it. Sit and bask in the glory of how easy the diagnosis is. Check the battery, make sure it's good. Check the voltage drop on the power side, voltage drop on the ground side. If all 3 of these test good, all you have left is a bad starter. That's it. Now you can get down there and rip that dang thing out of there and replace it. And as I write in my paper, it says, Mr. Webb, what's wrong with the starter? And I'd say, to put it bluntly, I don't care, and you shouldn't care either. Technicians in the field no longer rebuild the starters because it takes way too much time and money to do that, and starters become more specialized, and they're built by machines most of the time. So we don't do that in the field, and that makes it not your concern. What's wrong with the component, i.e. the starter, you should not care. That's what the job of the rebuilder is for. I mean, you can tell what's wrong with the starter. There's ways to listen to the crank speed. There's a way to get the smells. You can hook up scopes. You can actually hook up oscilloscopes and figure out what's wrong. Is it the commutator bar is wearing down or the brush is worn down? You can do all of that. But that is way more work than what they're paying you for. A starter diagnosis gives you 1 hour. 1 hour of labor time to diagnose why that car doesn't crank over and start. And if you take 30 minutes to figure out what's wrong with it, that's pretty good. You'll still get paid pretty well. If you take another 30 or 45 minutes to figure out what's wrong with the starter itself, who cares? They're still only going to pay you for an hour. They're not paying you to rebuild the starter. They're paying you to diagnose the starter, and if you're lucky, they're paying you to pull it out and put a new one in. That's it. This is really how simple starter diagnosis is. You do not need to overthink this. I start this section out by showing you how the starter works with the commutator bars and all the different parts, so that you don't look at a starter and think that the dang thing is magic, that there's just, some kind of voodoo happening inside of a box. You should really know how magnetism works. But when we get to the field and get our hands dirty with the real world stuff, you just need to know some simple stuff. Check the battery, voltage drops and voltage drops. And if those all check out goes the starter. It really is that simple, folks. I don't mean to oversimplify it, and I'm really not. But you don't need to overthink the diagnosis on this. The hard part for diagnosis, as we went over before, is going to be when you get more than 0.3 volts on, for example, a power side. So if you get like 1 or 2 volts dropped on the power side, that's where the nitty-gritty harder diagnosis comes in, because then you have to check back on your actual oh my god, you need to check your circuit. So that means, you know, you got to be able, is the problem here? Is the problem here? Is it here? Is it something wrong with this? Is it down here? Is it right there? Those are not too hard to work out, but that's where the hard diagnosis comes in. But to actually diagnose a bad starter really isn't that bad. It's just 3 steps, guys. That's it. It's 3 simple steps. So with all that said and done, what we're going to do next is we're going to move into the last 2 parts of the lab. First is going to be removing and installing the starter. I'm going to walk you through those steps. And then afterwards is diagnosing the no start. So I'm going to have you pull the starter out and put it back in first. And then we're going to jump back to the starter diag we just covered now. And I'm going to show you live on the actual car how we're going to do it. So that's what's going to be coming up next. Stay tuned. Now you finally get to do something after sitting through that whole long lecture. You finally get the hands-on part. You did it. So here we go. So as we move into the starter removal, I'm going to give you the notice up front. If you guys cross-thread a bolt in this station, I will fail you. This entire station is built to help you avoid cross-threading bolts, which is why we give you a stubby wrench, which is why I give you explicit call-outs in the video to avoid cross-threading. I have no patience for it. It's a monster and a half to fix if you guys do it, and the only reason you would cross-thread anything in this station is if you're rushing and not paying attention to what I tell you. It's an 8-minute section on how to get the starter out. Take your time, ask for help. That's why we have you do it in practice and not test. If you need assistance, come get it. We will help you with this, but no cross-threading the bolts. If you do, I'm failing you, and I got no patience for it. So I'm giving you the heads up right now. So let's go ahead and jump into it. So our first step for starter removal is going to be disconnecting the negative post of the battery. This way, we're not going to shock ourselves or hurt ourselves with electricity while we're trying to pull this starter out. So you grab your socket, your proper ratchet, just loosen it up, righty-tighty, lefty-loosey. You're going to take the nut off, and then pull the ground cable nice and far away from the battery terminal so we have no problems. You're going to take the nut. I recommend you put it back on the post so that way you don't forget it or miss it. It's an easy way to do it. Just do it by hand. So what we're going to do next is I'm going to have you take a drop light. I'm going to have you place it in the back over here because it's going to help you see a little bit easier when you crawl underneath the car and have to get the starter. So if you put the drop light about yay of so here, you get a little bit of extra light from the top, and you should be able to use a flashlight from the bottom if you really need it. So just get it nice and snug back there, nothing too crazy. You'll have some extra light. So next, you're going to have to get underneath the car, whether it's on the lift or you got to do it on your back, and we're going to find the starter. So I'm going to show you where the starter is at on this vehicle. So you got a nice slow shot, so you get it nice and slow, and it's not confusing where it is. You should see the exhaust pipe right there, and above it, it's going to be our starter. There it is. You should see a little blue test point, the starter itself. I'm touching it with my big old gorilla arms right there. That's the starter. That's what we need to get out. Now, on top of this starter is going to be the trigger wire. So we talked about trigger wire is, you turn the key and it engages. The trigger wire needs to come off of this, which is right here. There's a tab. Push down on the tab and then pull back on the connector. Tab down, pull back. Okay, don't go crazy and ripping it out. Just push down on the tab, pull it out, and swing it out of the way. It's going to be the first thing you disconnect on the starter. You want it out of the way so you don't go ripping and tearing it out of place. So now I'm going to show you the bolts that need to come out of this thing. There's going to be 3. There's going to be a nut right there on the top. It's the power wire that goes into the starter, so it's the main feed in. You're going to have one of the hold down bolts on the bottom. Notice there's a bolt to the left of it. Not that one, this one. Yeah, that's the one. So that's the one you want. So we're going to get that bolt out of there. And then there's going to be one after, which should pan up here. Oh my goodness, I'm doing it. I'm panning. We're going to zoom. And there it is all the way at the top. It's going to be a really long bolt. That's going to be the last one. So we need to get those 3 out because that's what's going to be anchoring the starter into place. So those are our targets. So I'm going to set this up here on the stationary camera. I'm going to pull these out. So first, I'm going to get the nut off of that power wire. Again, righty-tighty, lefty-loosey. Get the right socket. Make sure you loosen that nut because we're going to have to pull it off. So eventually it's going to loosen. You can just take the socket by hand like I'm doing because I don't like using the ratchet all the time. You just turn it and it just comes right off. You're going to pull it forward off the stud and just, again, swing it out of the way so that it's not, snagging on anything so we don't have that problem. So what's next, we're going to get the bolt here on the bottom. Again, Just get the right one. Don't try to get the wrong bolt. Just break it loose. It's gonna be, it's gonna be a little tricky depending on how strong you are. You have to put some, elbow grease into it. But break that bolt loose with your ratchet and go ahead and, just kind of get a couple of the threads out. Do not pull the bolt all the way out. Just loosen it, because we need to loosen the top bolt right there next. So the bottom bolt's loose. So now we're going to get to the top bolt. Yes, this is going to be tricky. Yes, you're going to have to do part of this blind. You're not going to be able to see it very easily, but you should be able to feel these bolts. So it's going to be in pain. Don't get discouraged. Get the socket on there. Loosen it, again, counterclockwise, and you should be fine. With that loosened out of the way, I'm going to use this by hand, get the socket up there. I'm going to loosen that bolt until it comes all the way out. So, top bolt out, there we go. I'm going to do the same thing for the bottom bolt that we loosened. The trick is you're going to have to put your hands on the starter, a little bit. If the bolt doesn't want to let loose, you got to jiggle the starter like this. It's going to help the threads come out of the bolt. So don't be afraid to move the starter a little bit. It's going to help you get it out of there. And once we loosen it up, we can get it out, using the socket by hand. And you should be able to get the bolt out. Make sure the starter doesn't fall out. So we're going to reach out and grab the starter with both of the bolts out and the nut disconnected. Get a good hold. It's a little bit heavy. You're just going to worm it all the way out of there. Nothing too crazy. Just kind of snake it out. You'll be fine. Don't drop it. Don't drop it. There it is, all in good shape. Hopefully nothing broke. Make sure you take it, set it down on your table or your bench somewhere nearby. You're going to have to do this because this is going to be your first sign-off point. So you're going to stop. You're going to get a signature for removing this before you continue, okay? So get the signature, go get it now, and then we'll move on to the install. Okay, so install. Make sure that's pointing the correct way. Notice that the gear teeth need to be pointed towards the front of the car. So that way we have a proper install. Don't flip it the wrong direction. And you're just going to snake it back up in there, sort of the opposite direction you got it out. I'm going to switch angles here real quick to show you the port. So we're going to reach it up in there, and you're going to try to kind of wiggle and jiggle it till it seats in there. See, like that. So the bolt holes kind of line up. Once you've got that in place, you're going to have to use one hand and use the other to get the bottom bolt to line up. So you're going to have to move the starter a lot to get that hole to line up. And again, this is going to be tricky because you can do it blind, but you need to get that bottom bolt in. It needs to catch a few of the threads. You should do this by hand, not with a ratchet, until the bolt sinks in and then catches threads. You're going to tighten it. So clockwise, you're going to turn it until the bolt, goes in just a tiny bit. Don't run it all the way down, just a bit. See how it holds it in place? Fantastic. Once the bottom bolt is in place, then we're going to get the top bolt. We don't tighten the bottom bolt because we need a little bit of wiggle space to get the top bolt in. So you're still going to be using your other hand. You're going to be moving the starter to get the bolt hole to line up with the big bolt. And you're going to do the same thing. You're going to have to get a couple of threads in by hand. Once you've done that, then you can go back to your ratchet and you can start to tighten these down. So you're going to kind of like tighten the bottom one. You're going to start tightening up the top one. Don't ratchet them down too hard. You just kind of snug it until they snag all the way and they bottom out. And once they've done that, so once you've snugged the bottom, snugged the top, now you can tighten the top. So you have to put some oomph on it. Don't slip. Make sure your hand doesn't slip on the ratchet. You don't have to, muscle man Honda that sucker in there just a little bit. And you're going to do the same thing for the bottom bolt. So you're going to take your ratchet, now that you've snugged the top, and now you're going to do the same thing for the bottom. We're going to tighten it down. Again, don't get crazy monkey strong on this. Just put some elbow into it, and the bolts will be fine. Be careful where you're leveraging your hand. Make sure you're not pushing on any of the electrical connectors. Once you've got that, then you need to take the power cable and put it back on that top stud, just like so. And then you're going to have to take the nut. You have to put the nut back on. This has to be done by hand. Don't do it by ratchet. You should catch some of the threads so you don't cross them. Once you have it on there, then you can get to the ratchet and you can snug it down. Snug this, again, don't wrench on it super hard. Just make sure that the nut stays tight. So with that in place, we're going to put the trigger wire back in place. The connector tab, the one that you push down on to get off, needs to be pointing up. And then we're just going to slide it like any other connector until it clicks. So it should click into place and you can tug on a little bit and it shouldn't come off. Now at this point we're going to stop and you're going to go get a signature for the starter install. So lab staff, instructors, or faculty are going to stop. They're going to double check your work. They're going to see your bolts are in the right place. They're going to make sure that your power wire is connected and that your trigger wire is in there. So they're going to check over it. As long as the install is good and clean and nothing's cross-threaded, because of course you didn't cross-thread anything because you're great and you would never do that. That would be terrible, and of course I would have to fail you out of the station for cross-threading things, right? And we don't want to do that. So make sure you go and get that signature, have them check it out, and then kick on to the last part. Once you've got all of those connected, you're going to get back to the top of the vehicle. You remember our battery? Yeah, that's the one. We're going to take the nut off, and we're going to reinstall the cable, so that way we can get this to start. So put the cable on, it's going to spark a tiny bit. Yep, there it is. So get the cable down, get the nut down, tighten that, and you shouldn't have any serious problems. Again, do not go crazy tightening this down. It doesn't take as much torque as you guys think it does to get this on here. So make sure you're getting it snug, but don't go crazy. Just a little bit. See, 2 fingers, done. That's all it takes. Make sure you move your drop light because we're not going to need it anymore, so that way we get it out of the engine compartment. It's safe back there. There's no pulleys to hit it, but just get it out of the way. Make sure none of the bugs are set. So you got the practice bugs should be all set to the top. Is good. So you're going to take your key, you're going to get in the car, you're going to put it in, you're going to turn it, and I'm going to play the sound. This is what it should sound like. You should get a nice clean starter engagement. It should start the car. It should, whir up nice and easy. No grinding, no clunking, nothing like that. Just a nice smooth engagement that tells you that everything is fine. That's what we're looking for, nice and clean. And here's the spot for your last signature. So you're going to stop and you're going to get a sign off for the car actually cranking over. That's the last thing that we require of you. So once you've gotten that signature, you are done with the starter R&R, which is the remove and replace. You're only doing this once in practice. So if you've got it now, you got it set. We're not going to test you out on this, just doing it once in practice. So if you got those 3 signatures, you're set. And now we're going to lead you in to the holy grail of diagnostics. I'm going to show you how to set the bug and diagnose it to get your last signature and finish out the lab. Okay, since we will be diagnosing a specific vehicle, we need the specific wiring diagrams for this, and this is going to be our Civic. So I'm going to show you how to pull them up on ProDemand, and I'm going to walk you through how the starter system works from a wiring diagram perspective before we go in there and start diagnosing with our DVOM and our scan tools if needed. So on your desktop, you're going to have ProDemand Automotive Repair information, so you're going to double click on that, open it up. It should come up in the web browser. I believe it will auto log you in, so you should have no problems, and you should come to the ProDemand screen. Looks just like this. So we're going to go select vehicle. You're going to go to vehicle selection, and we're going to select a 2016, not 2018. Pick 2016. And we're going to pick 2016 Honda. So you got make. The model is going to be a Civic. Your engine on this is a 2.0. The submodel is an EX. And then it should automatically select the CVT automatic transmission for you. Once you have that, click Use Vehicle. We'll bring you to this screen right here. Once we are here, we're going to type into the search box at the top here. We're going to type in Starter. And then we're going to hit Enter, or we can hit the little spyglass. It's a spyglass, not an hourglass. I always want to say hourglass. Once that pops up, we're going to have search results. So go ahead and click on Starter to the left. You have a bunch of options, TSBs, top repairs, causes and fix. What we are concerned with is the wiring diagram. So you're going to pick the wiring diagram down here, and it's going to show you in the upper left-hand corner starting charging system. So at the very top, figure 1, this is a wiring diagram for the charging circuit. We don't want that. That's going to be for another lab. So you're going to scroll down, left-click, and go all the way down, or you can, roll your little mouse wheel. Figure 2 is starting circuit W/keyless access system. This is starting circuit with keyless access. We do not have keyless access on these models. They're not. So we're going to skip these. One of 2. There's going to be 2 diagrams. There's 1. There's 2. So the next diagram is starting circuit without keyless access system. This is the one we want. So you're going to left click that. It's going to bring up this whole diagram, okay? So let's walk you through this, show you how this system's going to work. So in the left-hand corner, we have the plus and minus, so we can zoom in and zoom out. So I'm going to zoom in just a little bit. Then you're going to select the little hand icon. It's called the pan button. And that way, when you left-click, you can drag the whole diagram around, okay? So I'm going to zoom out just a bit. I'm going to pan all the way down here. So This solid line around here, it says starter. This is the starter itself. You'll also notice the battery is right here. If we look at the wire coming off the battery right here, this black wire comes down into the starter. That was that big wire that you do a voltage drop test on, right? So that's what that wire is. And notice that we have a cutaway. This is a magnetic switch. This is a relay. We just did relay, so we know exactly how this works, right? Once the relay engages, the switch will click and the motor will turn on. Here's the complicated part. We gotta follow the circuit to see how that relay turns on. And I'm gonna walk you through it. So we're gonna go from the battery. I'm gonna follow this black wire all the way up. I can left click it, it'll highlight for me, which I like. And it's gonna go into the underhood fuse relay box on the left side of the engine compartment. This dashed line outside, this means this is part of a really, really big component. This means this is just one slice of the actual fuse box, because we can't put the whole thing in the picture. But it's going to come in through the fuse box, and it's going to go through fuse 2-2, which is a 50 amp fuse. That's what that means. Fuse 2-2, 50 amps. So that's a symbol right there for the fuse. So it's going to go through this. It's going to go through a white wire. So you're going to notice that we have colors. BLK is black, WHT is white. And it's going to go back through part of the under fuse relay box. So it's going to come up into the green wire and go into the ignition switch. So you will notice the diagram for the ignition switch: lock, accessory, on, and start. So if we turn the key all the way to start, that's going to click, 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 and then it's going to complete the circuit. So we can still keep going, assuming we're in start. Once we do that, it's going to go through a yellow wire. Let's go back down into the under dash fuse relay box. It's not going through any fuses or anything, because there's nothing we see here. It's just telling you it goes to the box. Stays as a yellow wire. And then it goes into the relay circuit board. So this is a new enough car that there isn't a physical relay. It's actually a board. We'll show it to you a bit later. It's going to go into this board. This is another relay. That's right. We have a relay to control a relay. It's just relays all the way down. Relayception, if you will. So there are two paths for these wires to come out. So we go in. It's going to come through. And then we need to trigger the actual other side of this relay. There's going to be prerequisites. So let's take a look. So we got the yellow wire comes out. We have MT and CVT. This is for manual transmission. This is for the CVT. We have a CVT, so we're going to follow CVT. All the way down, it's going to go to connector 207, which is what that means. So we're going to be another connector there. It's going to be brown wire. And then it goes into the transmission range switch. This is called a Prindle switch, PRNDL kind of switch. And this is to make sure that you can't start the car if you're in drive. So that way you need to be in park or neutral to make it happen. And you'll notice this, we have low, S, D, N, R, and P. So we have park and neutral. And as long as we're in park or neutral, power will come in, go down through this switch, and then find the ground at ground 201, which is on the top left side of the transmission. So as long as this is in park, what's going to happen is when we click this over, click, click, click to the start, power comes in, goes out. This relay will energize. It'll turn the switch all the way up like that, and then we'll have power come out of the gray wire. It's going to come all the way down to connector 206, turns into a black with a white wire, which is the trigger wire, which will finally kick over the relay for the starter. That's what's happening. Yeah, see, this is quite the path, isn't it? Because we're going to start all the way at the battery, we're going to come up. Basically, we go through a fuse, we go through an ignition switch, we do go through a secondary relay. It's going to go through the transmission range switch. As long as the range switch is fine, then that will send power all the way to the trigger wire at the top of the starter and start it. So it's a bit more complex, obviously, than the system I gave you earlier, but it's not too complex. The only thing that's really new is the relay circuit board instead of just going directly through the Prindle switch. So if you have any concerns or any questions about how this diagram works, you can stop, go back, watch me explain it, and if it still doesn't make sense, get help, because you're going to have to know how this diagram works and how the trigger wire, that black with white wire, that connector there, is going to get power to actually click over the relay in the starter and get it to start, because we're really going to need that for the diagnosis. But that's what we got. Let's go ahead and jump in, and I'll show you guys how to start diagging. Okay, so we're jumping into the no-start diagnostic for the starting system, and in this case we're going to set a bug. I'm going to walk you through how to diagnose a no-start, and then I'm going to show you how to fill out the work order. So with all that said, let's go ahead and jump in the work order, because that's where we're going to start. So here's our practice work order for the starting system. And always at the top, we're going to start with the customer's complaint. My car will not start. I turn the key, but nothing happens. So the customers come in, they're like, oh, I turn the key, it doesn't start. What's wrong? That's what we have to fix. That's what we have to solve. That's what our mission is here. It says at the top, your job, verify if the problem exists, and if so, figure out and explain why. So we need to first start by verifying the complaint. Does the vehicle crank over when we turn the key? Yes or no? This is a really important first step because sometimes customers will complain that there is a problem, and when you go to see if the problem is really there, it's not. Like it starts, it turns over, maybe the customer doesn't know how to put the car in park before they start the car. So you always need to verify it exists before you just jump right in for diagnosis. So we're going to start now by verifying the complaint, and then we're going to move into isolating the cause of the problem. So on the side of the Civic, we have our test bugs. You're going to flip this one down, the first one, which is going to enable your test bug. So you're going to take it, you're going to go into the car with the key, and we're going to verify the customer's complaint. So with the bug on, because you should have switched it, put the key in, we're going to turn it, and we should get a no start. So you turn it, you don't hear anything, nothing happens, right? So there's no start, customer's right, put the key in, nothing occurs. So we verified that problem exists. Make sure you double check that your car is in park. Sometimes it won't start if it's not in park. And once you got that, we're going to hop out of the vehicle and start our diag. As covered in the battery station, all diag starts at the battery. So we're going to take a DVOM. We're going to check for open source voltage. We should have around 12.4 to 12.6. So double check your battery and make sure it's there, because the battery's too low, it's not going to start. My battery's pretty good at 12.4. That is enough to go off of. So we know the battery is, for the most part, good to go. Not our concern. So the easiest test to run right now is to see if the trigger wire on the starter is actually getting any power to click over the relay. And to do this, we're going to have to hook the DVOM up the way I have it on screen. You're going to take the negative to the negative on the DVOM lead to the negative post of the battery. You're going to touch the positive lead of the DVOM to the input wire for the starter relay. And then we're going to turn the key, and we're going to see if we get any power that actually flows there. And that's going to be our easy start test to go. So let's show you how to do that live right now. So we got our handy DVOM. We're going to set it to the volts DC scale. I'm hitting the range switch a few times to change the decimal place of my voltmeter so that it reads a little faster. You can do this if you wish, but you don't have to. It will auto range for you. Then we're going to hook it up just as I showed in the previous diagram. And make sure we're on that negative post right there. And then we're going to take the other lead, and we're going to drop it down back behind the engine right here. You're going to have to drop it down because, of course, you're going to have to crawl into the vehicle and hook it up. And once it's all the way down, you should be able to get underneath it, and you're going to hook it up to the trigger wire adapter that we have right here. Once that's hooked up, you can come back up to the vehicle, make sure everything's hooked up the way that it's supposed to be, and then have someone turn the key, or you can turn it yourself. You're going to watch for voltage. If you're going to turn it yourself, you can actually move the DVOM the way I have like this, which is what I had to do because I didn't have a helping hand right here. And I had to flop back into the car just like this. And when I do, I can actually see the DVOM through the window, and it makes it easier for me to test just by myself. So you should be able to see it, turn the key just like that. And in this case, I get no voltage down to the trigger wire at all. Which on the diagram looks something like this. We're going to get 0 volts down to the trigger wire with the DVM hooked up this way. Which means something's wrong, something's breaking somewhere in the circuit and not feeding enough power to the trigger wire. So I'm going to jump right here and show you where some of the potential problems could be. So pulling back here, we can see that we might have a problem, for example, with the transmission range switch. Is there power going into the transmission range switch? Does the range switch itself work? And is the ground side okay for the range switch? So that's going to be one of our big concerns. And then moving a little bit north here, we might have a problem with the relay circuit board, power going into the relay circuit board and coming back out, so the circuit board could be bad and so could the wires. We might have a problem with the ignition switch itself, though I will admit that is unlikely because we got the dash gauge to light up. And of course, we might just have a problem with the fuse over here. So the underfuse relay, the 50 amp one, could be a problem. I'm going to show you how we check the fuses and the circuit board. It's tricky on this one because they're not easy to test because of their design. This is not like a normal car. And then we're going to focus on the Prindle switch, and you're going to see why real quick. So let's start with visually identifying that relay and the fuse. It's going to be underneath here in the fuse relay box, which you can pull up from these tabs, flip it over and turn it, and you see the box with all the fuses, etc. here. When we want to identify fuses, you can always look underneath the side of the fuse box, and you'll have like a panel readout that shows you where just about all the fuses are and what their values are. So you have 50 amps, 40 amps, so on and so forth. You'll also have these numbers 2, 1, and 3, and 4. And these are giant block fuses. These are fuses that come in huge cubes and can't be pulled out like these tiny ones over here. Let me show you real quick. So if we look inside the box, we have these big chunky fuses. They're one piece. You get the small ones and then you get the big ones. The starter, trigger, relay, and the fuse itself are housed in one of these larger ones. So we can't actually test them individually without completely removing them out of this box, which is a very difficult task. So it's a little tricky to get these fuses out. So we're going to treat that as a bit of a last resort because of how difficult it is. At which point, we're going to show you the relay, and it's also a giant square. It's not a single relay that we can test. This is also hard to test. So we're going to skip over that, and I'm going to show you how to get to the Prindle. So we're going to check the Prindle first. And the easiest way to do it is you're going to disconnect that MAF sensor. You're going to take the tabs off of the airbox, move it out of the way. The entire lower part of the airbox itself is not bolted down. You just have to wiggle and jiggle, and it should pull up and out of the way. Once it's out, you're going to set it aside. Don't forget where you put it because it's going to have to go back in and you don't want to damage it. And we need that out of the way to get to the Prindle switch, which is right down here. So if we dig down through this mess of wires, we can see the transmission range switch, again, call it a Prindle a lot of the time, right down here. It's got a little locking tab on the side, it's got all the wires that are going into it, and we have 2 test points on it. So these are my wire piercers that I've set up to make your tests a little bit easier. Again, if you remember from the wiring diagram, I'll pull it up here real quick. That's what the Prindle looks like. So it's got a brown wire in for power, and it's got the black that goes out for the ground. That's why I have the 2 test points there, so we can check to see if power goes into the Prindle, and then we can see if power is coming out of the Prindle properly through the black wire to the ground. That's what those 2 test points are for. Before we start this, we're going to have to disconnect the Prindle switch, and this is going to be a bit trickier. There's a tab right here that will pull up, so I've already pulled it off myself, so you got to lift on the back of it and then push back, and that will disconnect the locking tab. Now here's me doing it in real time. So if we go down, we're going to take your tiny little flathead screwdriver. You're just going to pull back on it. Be gentle when you're doing this so you don't snap the tab off. It is a lot easier to do than you think. You should just feel it pull up and then you can disconnect just like that. And the connector should move gently right out of the way. Again, it's that little tab right there that you need to lift up on like that, and then you'll pull it back out and it'll be just fine. So back to the diagram side of things, this is how we're going to have to hook up the DVOM in order to see if there's power going to the brown wire. Negative goes to the negative side of the battery. Positive is going to go to the brown input wire to the Prindle with it disconnected. We're going to turn the key, and hopefully we should see some voltage go into that switch, which means everything leading to that switch is good. So showing you live on the car, if you're looking for the brown wire for the Prindle switch, it's going to be one of our test points. Flip it over, you see the brown wire, no tracer on it. That's where we're going to be hooking the meter up to. So here I am up top. I'm setting my meter to volts, DC, not AC. I'm setting my range a little bit because I want a faster reading than usual. Negative is going to go to negative, so there we go. And then I'm going to take my test lead. It's got an alligator clip on it, so I'm going to take it off. So unscrew it, righty-tighty, lefty-loosey. Be aware the tips are sharp. You can hurt yourself. Set this away and don't forget where it is. Do not put it in your pocket. Don't walk away with these.
So this is me coming at you from the future with my much sexier, sultrier voice with my better microphone to point out that on these Civics, I have put extension pigtails on for the wires I'm about to show you how to test. So you see the brown wire and the black wire that go all the way down there. These are pigtails up high, so you don't have to get down at the connector. Test at these new pigtails, okay?
All right, so with this set, we're going to go ahead and run it into the test points. Do not jam it into the connector, by God. And once it's in there, we're going to sit and turn the key and see if we get any power into it. So I got my connector set up, turn the key, and I see voltage. Hey, look at that. That's pretty good. That is, in theory, exactly what we want to see, power going into the Prindle switch. All right, so let's go and review on the diagram real quick. So this is what we got for a reading, 12.6 volts or about yay if so. This is a very good reading. That means all the wires leading up to that brown wire going into the Prindle switch, the fuse, the actual relay, the relay circuit board we showed you, the wires, all of those are good because they're delivering power all the way to that brown wire, which tells us the rest of the circuit and the fuses are good, which remember, the fuses and the relay are hard to check. So now we need to be able to check the ground side, and I'm going to show you how to hook that up real quick. So here's our hookup to check the ground side. All we did was move one test lead over from the brown wire to the black wire. And we're going to do this with the connector plugged in. It needs to be plugged in because power has to go in through this brown wire, go through the prindle, back out through the black wire, and then to the ground. So the actual connector needs to be plugged in for this test. And we're doing a voltage drop, which means we want to see what the difference is between point A and point B, which if there is no resistance, there should be almost no voltage drop. If we see too much, like more than 0.3 volts loss, we know we've got some kind of open or too much resistance there. I'll also show you how to do an ohms test if necessary. So this is what we're doing for a hookup on the diagram. Now let's go show you how to do it on the car itself. So just like I mentioned, we're going to have to go down and we're going to have to reconnect the connector. So go ahead and plug the prindle back in. Make sure it lines up. Don't jam it in there. It should just kind of click into place and the locking tab should go. Very pretty. Just like that. Beautiful. So we're going to take our DVOM again, set it to the volts DC scale. And we're not going to have to move where the negative lead is at, remember, because it's still in the right spot. And then what we're going to do is we're going to take the positive test lead and check that black wire. Now, without even having to turn the key, we get 12 volts loss. That's a voltage drop of 12 volts between the 2 points. That means there's a huge amount of loss there. And let me prove it to you. So we're going to take the test bug and we're going to turn it off and see what we get. So turn it off. Look at that. The voltage drop almost all but disappeared. Not too bad. Flick it back on. There it is. It's alive and well. So that's how we can see that real quick for voltage drop. So again, checking the diagram side of everything, we can see that we have a massive voltage drop from point A to point B. It's too much. I mean, it's so high that this isn't even too much resistance. This has to be an open because we lose all the voltage between these 2 points, which means somewhere between here and here, we have an open, and we need to find out what that is. I'm going to show you real quick how we're going to test this using an ohms test. So if you want to verify, just to double check, you can ohms test this wire all the way out. Remember the ohms test? Because you finished out the DVOM board because you had to do it before you got here, right? So I'm going to show you how to do the ohms test real quick so we can double verify that this problem exists. So we have our DVOM hooked up most of the way that it is. We're going to set it to the ohm scale, just like that, not the volt scale, ohms. And just as before, we got the negative connected to the negative, and we're going to touch the positive to that black wire coming out of the prindle. We should see some continuity here, some resistance because the bug's on, and we're going to touch it. We're going to see, and look at that. We got nothing. It's out of limits. Too much. So we're going to turn the bug off, and look at that. We get continuity. There's a little bit of resistance, 8 ohms, but there is continuity. As we flick the switch on and off, we will see continuity exist and then not exist all over again. So we can use the ohm test to double verify that there's an open or a break in that wire right there. So with all that knocked down, we should now have enough information to conclude what the problem is. And this is how we're going to be filling out work orders. And this is how I'm going to fill out the practice work order. You're going to do it along with me. So down in the cause of problems, what is the cause of the customer's complaint? Write a short paragraph explaining what the cause of the problem is and back your conclusion with evidence. So I wrote, there's an open in the ground circuit of the prindle, transmission range switch. That's my plain English explanation to a customer or my service writer why the car doesn't start. There's an open. It's an open on the ground side and it doesn't start. Okay, says the shop manager. How do you know that? So we've plain English explanation. Now we need to back with evidence. My evidence is that I performed a voltage drop test and found 12 volts dropped on the ground side of the circuit. That's why. That's how I know it is. Not only can I tell you there's a problem, I tell you the evidence that backs it because your shop foreman's going to want to know this kind of stuff. Doubly so, I also performed an ohms test on the ground circuit and found it to be open. I got an OL reading between the ground side and the battery. So that's how I back that up. Make sure you plain English explanation, then back it up with evidence. Second part, correct the problem. What would you do to correct the problem? Write a short paragraph, explain what you do to fix it. This is very simple. Trace the ground wire to find the open and then repair it. That's what you would do in this case. Exactly where the open is at, you guys don't know. I'm not having you trace it down. It's too much work for a kind of practice lab right now. But that's what you're going to do. So this is what your completed work order should look like. Make sure it's filled out the way that I have it on screen that we just walked you through. And this is where you're going to stop and you're going to go get a signature for your completed work order. So again, make sure you go get signed before continuing, get that signature for the completion of the work order, and then you're going to finish it out by buttoning it up, which is what I'm going to walk you through right now. So your work order is all filled out. So you're going to go ahead and set the bug off. So you're going to flip the switch up. You're going to disconnect your DVOM. Make sure it's all nice and tidy. Do not forget the alligator clip. Put it back on and screw it. Make sure it's nice and tight. Do not lose this. You have to turn the alligator clips back in with the DVOM. Don't lose it. So I'm going to set my meter aside. I like to wrap mine up just like this. Keep it loose. Nothing too crazy. Set it aside. Go ahead and grab your air box because we're going to prep it for an install. But before we put the air box back in, we got to reconnect the brindle switch if it is disconnected. So for whatever reason yours is disconnected, make sure you put the brindle back in, slides in, make sure the lock tab goes in place. You'll hear it click. Once the brindle's in, air box goes back. It's got a set of tabs here, here, and here. And you got to line those up, and you got to drop it down. There's not going to be any bolts. There's not going to be any nuts. You just got to make sure you line the holes up and drop it down. It's kind of a pain. You'll see me sort of struggle with it a tiny bit, but you got to move it out of the way. Sometimes you got to wiggle jiggle just to get it to drop down. Try not to crush the air filter while you're doing it, please. And then once it lines up, it should drop down into place. Shouldn't be too much drama. I say that, but I got a little bit of drama getting mine in here. I keep this in and don't edit out so you can see that even I, master technician Skylar Webb, can sometimes struggle to get an airbox back in. This is how it works when you gotta fix stuff, right? So once that's down in place, you're gonna take the airbox lid, go ahead and set it right back on top. It's got the little tabs, so line it up, and then push the tab up, push the tab up. Don't forget the connector for the mass airflow sensor. You're going to put that back in. If you don't, the car's really not going to have a good time. Double check your battery connections. Make sure everything's pretty good. Don't forget your screwdrivers or any loose tools. And that should be pretty much set. Double check. Make sure everything's nice and secure. That your bug is set off so your practice bug isn't on. And then you're going to be good to go. You're good to move on to the next section and make sure that everything is all good. So let's go ahead and clear this out. So we're at the back end. You've made it. Oh my God. Hit the ground and kiss it because you've made it. So what we're going to do is we're going to go over our conclusions to wrap this sweet, sweet station up now that you guys are all masters of actually diagnosing and pulling starters. So our first conclusion, what you should walk away with, is that magnetism operates off flux lines, which permeate through everything. Nothing can completely stop flux lines. Like the unending force, like death, it will find you. And once they permeate everything, they cause magnetic pulls on objects that are prone to magnetism, such as metal objects, typically speaking. Plastic, for example, is not drawn in by magnets. Metallic objects are. The second one, magnets can be created or they can be strengthened by wrapping your wire around them and pumping current amperage through those wires. That allows us to control the intensity, strength, and the distance of flux lines with electrical current. So again, this is how coils are generated. We take magnetic objects like solid earth magnets, wrap copper or aluminum wires around them, run power through those wires, and that will increase the strength of the magnet. This allows us to pull or push objects harder or from greater distances based on how many windings we have and how much power we pump through them. Number 3, opposite poles attract, similar poles repel. Man, I totally typoed poles right there. Haha, you're not going to find that in your paperwork. So opposite poles attract, similar poles repel. And by switching the polarity, i.e. the direction that we push the electricity through the wires, we can cause the poles of a magnet to switch. So as we talked about in how electric motors work, by changing the direction from positive to negative through the actual coil windings, we can change the poles of the magnet itself. Okay? So be aware that that's something we can do. Number 4, the switching of the poles allows us to not only attract objects like in a relay, but also rotate them like in the motor, both of which are combined to create the automotive starter system because we have a relay in there and we have an actual motor. Both use magnetic principles, so you need to use magnetism to operate them all. Number 5, starters draw large amounts of current and thus need a fully charged battery to operate. Again, we should have 12.4 to 12.6 volts. Better have it, and that battery better be strong. We better be able to pass a load test or a conductance test. If you don't have a fully charged or close to fully charged battery, do not try to diagnose the circuit because the battery is the problem. Focus on that first. Number 6, more than 0.3 volts dropped from the battery down to the starter itself can cause a failure of the starter to function properly. That's our voltage drop from power side. Number 7, More than 0.3 volts drop from the starter back to the negative post of the battery can cause a failure of the starter to function properly as well. This is going to be our voltage drop on the ground side, so be aware of that. Number 8, if you verify that the battery is good, the supply circuit to the starter is good, and the ground circuit of the starter is good, yet the car still won't crank over properly, then you need to replace the starter. So let's reread steps. 9 says reread step 8. Step 10 says reread step 9. Boop, boop. Number 8 is the big takeaway. If you verify that the battery is good, battery check, first step. The supply circuit to the starter is good. Voltage drop, power side, is good. And the ground circuit is good. Voltage drop, ground side. The only thing that's left to go wrong is the starter. That just means replace it. What's wrong with the starter? Again, that's not something we're going to go over here. That's not your concern at this moment. If you can get the first test, second test, and third test down to verify if the starter is bad, you will be leaps and bounds and rocket ships ahead of other technicians in the field who barely even know how to work a DVOM. They look at it and they're like, well, am I supposed to lick it? I don't understand. No. First, second test, and then the third. Battery's good, voltage drop, power is good, voltage drop, ground side is good. That's your big takeaway on your conclusions. That's it. That's all that it is. I just have you keep reading steps 8, 9, and 10 over and over again until you're sick of it, which I'm sure you are right now. So those are our big takeaways, conclusion, and that's the finality. That's the end of the starter diagnosis station. Hopefully this helps. Hopefully this makes sense to you. Make sure that you have your signatures. The big signature points should be for the relay. You should have the relay operation that I have you set up on the board. You should have a signature for the starter being pulled out. You should have a signature for the starter being put back in. Keep rocking and rolling, and I hope to see you folks in the alternator section if you haven't already, because I recommend that if you have not done alternators, that's what you do next. So until then, folks, good luck and have fun.